This is April 15th. It's a beautiful Saturday morning. Spring, neither hot nor cold. I hope you would agree after a long time. We missed a couple of papers in the last one. So today we'll give quite some time to research papers in the afternoon. The two things that I would certainly like to do, if possible, is DistilBERT, which we have been using. It brings in an interesting architecture, and it's one of the most widely used transformers. So really worth learning about. And stable diffusion. Stable diffusion goes to multimodal learning using transformers. So in a very quick summary of what we'll do in the afternoon, DistilBERT is trying to learn from a larger model to create a much smaller model. And the purpose of that smaller model is it tries to maintain or retain most of the accuracy, performance metrics of the much larger model, but still being memory efficient, being much smaller, and computationally less hungry. In more practical terms, you want a model that runs fast on your laptops. Isn't it? It shouldn't be that the only place the model runs is if you have a workstation with no less than 2 4090s in it. So that's the point. And what is stable diffusion? And CLIP. Actually, we may do CLIP also, 3 papers. What these are interesting adventures recently that the transformers have taken with great success. CLIP, one of the early ones, one of the first ones, took this question: can we have auto captioning of images? Right? So suppose I show you an image, can it immediately say, put a good caption to it? Now, it is different from object classification. So suppose it's a cat or a dog. You can show a picture and it will classify it as a cat or a dog. That is computer vision, a classic sort of a classification problem, the normal classification problem. But what if you're holding a dog, right, in your hands? So can we go further? Now, if you remember, in the very first lab, we did something very surprising. We searched not for a cat or a dog, but we searched for very human emotions, right? We asked this question: can you search a visual library for things that represent a love of dog, right? Now, a love of dog is not a dog, it's an emotion. And how can you find images that sort of represent or are evidence of a person's love of dog? And we found that we could do that. The architecture. Now, if you remember that, how did we do that? As all great things that you accomplish in natural language processing, you have to line up many of the ducks. One of the ducks was the sentence embedding. The other was creating a vector database into which we could search, fast searches. The third one was, again, the CLIP. Right? Now, we have done SentenceBERT paper. We also understand what this approximate nearest neighbor is. We went through the theory, but we didn't do CLIP. We'll do CLIP. Now, the continuation of that is the next step. CLIP goes from images to text. It can give you a summary or understand an image, but can you do the reverse way? The reverse way is a generative process. Can you give it a prompt, a text? And from this, ask a transformer to paint a picture, represent a picture. And you could give it pretty absurd things. For example, you could say a cow on the moon reading a book. And it should be able to understand that cows won't survive on the moon unless they're wearing a big astronaut suit. Take an astronaut suit, dress the cow in it, put the cow on the moon, realistic moon, rock, and then have the cow hold a book in the only way cows can hold books or things. And yet get away by doing that. You saw that we did it, right? Or we could give pretty absurd things. Monkey carrying a chair while jumping from one tree to another. And well, I don't know if in real life or in the history of this earth, monkeys have ever done that, but they certainly can do it um, in the make-believe world of your Transformers. Right? And isn't it amazing that you can do that? And we went through all that. So we'll study the research papers. But today, we will go through, we'll continue the journey of transfer learning using the Hugging Face Transformer libraries. So to whet your recollection, before we delve into the labs directly, what did we say? We said that training a transformer from scratch are these large language models. The fancy word people use for transformers these days is language models. These are language models. And transformers are already ginormous models. They have like billions of parameters, hundreds of millions of parameters. And now if you say a transformer with 100 million parameters, a few 100 million parameters, people would scoff at you for using such a puny little model, right? You have to go not just billions, but hundreds of billions. And now has come GPT-4, which presumably, or we are told, is in trillions of parameters. And GPT-5 is about to come out, which is supposed to weigh in and no less than a hefty 2 trillion parameters, right? And what happens with these models is, as these models become bigger and bigger, two things happen. They develop emergent capabilities, things that models of a lower scale actually did not have. For example, they developed the ability to do arithmetic, to reason, to do things that prior models did not have. The other thing that it does, and which is something we'll delve upon, is that they become a bigger and bigger environmental disasters to train. The carbon footprint to train one of these large language models is astonishingly large. And that is one of the topics we'll talk about. The other thing that is happening, and it is a social phenomenon, there is a tremendous amount of euphoria and endless possibilities in the zeitgeist, in the current mood. People feel they have almost blind faith and optimism in this. There is talks of AGI having been there, that we are reaching points of singularity where this AI will take over, where many things would happen. Right? The fact of the matter is, you have to be extremely cautious. It's our social responsibility to be very, very cautious around these large language models, because they are deeply, deeply flawed. And we will delve today in one of the flaws that these models have that perpetuate historical stereotypes and biases. We'll see it with an example. Finally, we ask this question: if these models are extraordinarily expensive to train, then what is the way forward? And there, fortunately, we discuss the concept of transfer learning. Transfer learning says that transfer learning has a flavor of reuse or recycling about it. See, as good environmental citizens, we are told the 3 R's. Wherever possible, refuse to consume something. Right? So, for example, when you drink water from a plastic bottle, it's an environmental disaster. Actually, the water from the tap, the municipal water from the tap, at least here in California, in the Bay Area, has been proved scientifically to be far purer and more germ-free than the bottled water, which has a lot more germs. Think about it. It's stagnant water that's been sitting in a bottle, right? Cultivating germs. Whereas municipal water is running water that's just been purified. So first thing you can do is you can refuse to use bottled water. I'm just taking an analogy, right? When you do that, you don't you don't add to the environmental disaster that is the world of plastics and microplastics. It turns out that there will be no more any generation of living beings on Earth that won't be infused with microplastics in their bloodstream, in their tissues. That's the damage. People went to the deepest part of the sea, and in the deepest crevices, guess what they found? Not some exotic life form, but more plastic, right? So it speaks to the fact that the first thing we can do is refuse. The second thing we can do is reuse. Instead of drinking water from plastic bottles, perhaps we could get purified water from a store, but fill up our water bottles with it, giant water bottles, and then reuse, refill those bottles. That's what we do here at Support Vectors. Refill the water bottles. Next thing you can do, obviously, is recycle. If you are done reusing it, you don't need something like your soda can, you can recycle. Recycle is far more expensive, of course. Right? It goes through a whole process. Tremendous energy goes into reforming that metal into something else, or paper into recycled paper. So these are the 3 R's. In some sense, transfer learning has the flavor of reuse. What do? We pre-train to use the language of transfer learning. These models, once they get trained, we call them pre-trained models. The world makes it accessible. The whole world except OpenAI. It seems that they want to hold on to their models now. But most of the world open sources their large language models that they train. Once they become available, and Hugging Face is a great repository of those models that people make available, then what can you do? You look at your business problem, you look at the task you want to solve in real life, and you ask, does a model exist that addresses it? Already exists. There would be something either speaking to that task, something adjacent to that task, right? That is doing a problem that's slightly similar to that, right? So what you could do is you could download a checkpoint of that model, pre-trained model. Now, what is a checkpoint of a pre-trained model? Who would like to enlighten us? What is a checkpoint?
The weights.
Exactly. So what happens is when you take a neural architecture, it is a particular layout of the neurons and so on and so forth, the attention heads and so forth. But then initially it's all randomized. But when you train it with vast quantities of data, all of those weights, they stabilize or they become something meaningful. So that is what you call the learning. You go through the process of gradient descent and backpropagation, and they acquire certain meaningful values or useful values. Now, what you're downloading is of course the clue to which neural architecture it is, and more than that, you're also getting the weights they have been trained into. Right? That's your checkpoint. So a pre-trained model, more specifically, is downloaded as a whole bunch of weights. Once you get these weights, you can load it locally. Now comes the question. You apply to your task and see, does it give you good performance? Now, if the model was trained for that task, it would probably give you good performance. Now, here again, we have certain caveats. We realize that when you get the model, typically, it comes headless, isn't it? It's sort of, if you remember, and I will review this in the Jupyter notebooks in a moment, but let me just say it. It comes without the pre-processing unit, and it comes without a post-processing unit, a head. Right? Now, why does it so happen? Why does it so happen that it comes sort of bare bones like that? Right? Why does it come like that? Can somebody enlighten us? Why do we get these transformers, these pre-trained models like that?
Sure. You can give it an instruction.
Allow fine-tuning.
Based on what it has been trained on by.
Yes, you're saying your meaning is right, but you're not using the exact technical words. So let's give somebody else a try. Anyone else? The question is, when you download a transformer or a model, pre-trained model, say from Hugging Face, they typically are headless.
So you can fine tune it.
One reason is you could fine tune it, but you might as well have attached a head to it or a pre-processing unit to it. See, the reason is one trained transformer can serve many purposes, many tasks. If you remember, the original BERT paper mentioned at least 6 tasks in which that trained bird, just beat the state of the art, right off the park. It hit the ball straight out of the park on 6 of the benchmarks and 6 of the tasks. What it means is, and what these pre-trained models are often trained at, is something that you actually won't use it for. So let me delve a little bit more on it. Let's take BERT. If you recall, what we fed into BERT were 2 sentences. Right? And then there was a lot of attention and all of that multi-head and the whole, the mechanics of it. At the end of it, you get certain, all of these, like you can use it for classification tasks, you can use it for fill in the blank task, you can use it to infer whether the second sentence is a paraphrasing of the first sentence, you can infer whether the second sentence is an entailment of the first sentence. I mean, it is appropriate a follow-up to the first question, first statement. You can ask the question, is the second sentence an answer to the first question, the first sentence? And if the first sentence is a question. So do you see that? You are using it, or you could altogether avoid the second statement, fill it with padding and ask this statement, this sentence, does it have positive emotion? What is the sentiment of this? Right? You can have the sentiment on a scale of 1 to 5. You can have, as we did the last week, you can have 6 emotions. If you remember, joy, anger, sadness, and so forth. You could put it into those buckets, or you could just have a vanilla thumbs up, thumbs down, positive or negative sentiment. You could classify the text, the sentence. But remember, when we say sentence, we mean it in a more general way. It could be a whole paragraph of text, but in this NLP, we treat a sentence as basically a unit of textual input. It could tell us whether this text is about politics, it's about science, right? About programming, right? It's about religion. For example, the 20 News Group data set helps asks you to classify any given text by the topic it belongs to, right? And you could do many tasks. When you use a transformer, so the first thing you realize with these models is that once they get trained, you could use it for many tasks. Then you realize, now, wait a minute, how can I use it for many tasks? A classifier, for example, a binary classifier expects a logistic regression unit. Remember, cat or dog, right? Positive emotion or negative emotion, right? Science or politics, things like that. Or a more multi-class classifier would say, like, for example, emotions. It would say, is it joy? Is it sadness? Is it anger? Right? So you're classifying into, so then you're using a softmax at the last end. Right? If you're asking this question, fill in the blank, and you hit some word, it's a mass language model. At that moment, you're saying which word is likely to be here. So each of them, they have a different head that's making the inference finally, isn't it? And so what you would rather have is a headless model onto which you screw in a head the way you, for the purpose that you do. With that, it's a drill bit, yes. And I use the example of a drill gun, a drill bit, right? So
with your mouse, you come here. I told you.
Yeah.
Don't touch the mouse.
Yeah.
Look at me. Over here.
Okay, could you
run it? You will see this. Then click power this machine on.
Okay, hang on. Yeah. So if you look at a drill, power drill, right, what do you get? When you buy a drill, you buy a drill. You don't get any of the drill bits. But based on what drill bit you're using, you're either using it to work on a screw, put a screw into wood or metal, right? Different kinds of bits you would use based on whether you're threading, whether it's a star head, it's a flat head, it's a Allen kind of a thing, Philip head, and so on and so forth. Or are you using it to drill a hole? Or are you using it to tighten a bolt, right? All of them are different heads, different bits. And a drill gun is in itself useless, right? Or try putting it to your hand and just turning it on, it just will spin, right? It doesn't do anything. So that's a relationship between a pre-trained model and a task. To do a task, you need to put a drill bit in a drill gun. In the same way, to do this, you need to attach the proper head. Go ahead.
So you attach at the end, or you attach in the beginning?
No, at the end. At the end, it produces the output. It's the head that produces the output. So, for example, let's take multi-class classification. These layers, transformer layers, have produced, let's say, they will produce a whole set of these are called logics or potentials or values, or I always look at them as energies, right? With a more physicist bent of mind. They produce the different energies or potentials. Now, what can we do? We can pass it, if we so choose, we can choose to pass it through, a whole dense neural net, which we have as a classifier, right? Not just necessarily a softmax. We can choose to do that to further, add a few more training layers and then train that. Right? We take some data and train that last layer, the head. Or I can just attach a softmax and say, well, I don't need to do further training. Let me attach it and get the job done, isn't it? So we can do that. Now look at the back end of it. So this is the output end. You need a head at the output end. Now, what about the back end of it? Just as in a cordless drill gun, you need a battery. In the same way, you need something in the beginning of a model. What do you need? It expects data in a certain format, right? So, for example, if you're using BERT, it is expecting token it is not expecting text. It is expecting that the text has been converted to tokens, sequence of tokens. And in fact, the sequence length should be 512 in the standard BERT case, right? And there are other models like Big Bird, which expects 4,000 and so forth. And there are different things. You can look into that. So, and they expect that the beginning has a padding called the special token called the CLS. The end has, between the two sentences, you put yet another separator token, SEP, right? And at the end, you have you have padding token. And if you're masking a word, you have a special masking token and all of that. It is expecting the input to be like that. So you need a tokenizer that converts it into that format. And we went through the tokenizer. The tokenizer itself is a complex beast. It is not like your a basic string tokenizer that you use in, let's say, standard programming, C programming, Java programming, JavaScript programming, etc. It's a little bit more involved. In fact, it is itself an AI trained model that is smart at tokenizing. Right? So text goes into the tokenizer, for example. If you are doing text classification, from the tokenizer tokenizes it and gets it ready for the model. It goes into the model. Energies come out, or logits come out, right? There's potential. Those are further fed into the classifier network, which may be just a softmax layer or a logistic classifier node or something like that. A function, or it could be a few layers, something like that, or it could be whatever. Nothing prevents you from, for example, venturing out and saying, I'm going to put a gradient boosting layer, right? Or I'm going to put a support vector machine at the end of it. And you could do what you want from the head, because you get the hidden states. By the way, these words are all synonymous. The hidden states produced by the transformer, the logits, I call potentials, energies. Right? You may also see me use colorful words like voltages, right? so on and so forth. They are all the same thing. Right? Then they feed into the next actual classifier, and they will classify. And so you have a text classifier. The last classifier cannot classify text. It can only classify certain hidden states or certain hidden latent representation vector or potentials. Right? And what is a good potential? That potential represents a very semantically meaningful representation of the text. What knows how to create such a semantically meaningful representation of the text, of the sequence, text sequence? The transformer, because of its attention head. And the tokenizer has fed the transformer, right? Tokenizer feeds the transformer feeds the classifier produces the output. Do we see the relationship, guys? So that is what we have been doing. Now, where were we last time? If you recall, we went through the tokenizer in some depth. We realized that the tokenizer itself is a complex beast, right? And we learned that there are various tokenizers out there. For example, there's a BERT uncased base tokenizer, which uses a small base BERT model. I believe BERT base uses, how many multi-heads did it have? A puny little 12 multi-heads, I believe, right? Which today people will say, small, right? But actually it's huge. You don't need even, because when you load that model is ginormous. It's hundreds of megabytes, right? But and actually it's a phenomenal beast, even the base. But you could use large if you want, but that. And then uncased stands for all the tokenizer first converts all the text into lowercase, right? So it is not case sensitive. Go ahead, go through them. The first few notebooks are just the installation. Then we did the search, the AI search. We learned about Hugging Faces. So I'll start maybe Hugging Face introduction to sentiments and zero-shot learning and text generation, text to image. Do we remember the named entity resolution? We did that, visual QA. Then we learned about transfer learning. Let's go into transfer learning. And when we do that, we said that transfer learning is made up of two steps. One is the pre-training of a large model, right? And then saving the checkpoint and making it also available. If you don't make your checkpoints available to the world, then the world can't use it, right? Or the new way seems to be to charge a ton of money to use it through APIs. So, well, that's that. And the second thing is you can download the model and fine tune it. Yeah? So today, we didn't do the fine tuning. We did all the rest of the stuff. Just to recall what we did, we realized that Hugging Face comes with, first of all, the pipeline. You can use the pipeline API to do a lot of the work that you want to do. Do we remember that? The simple pipeline, ready-made, ready-to-use pipelines that would do many things. It also comes with a lot of classes. For example, let's look at the tokenizer stuff. We talked about the tokenizer last time. Now, if you go back and look at the tokenizer, it'll be very quick. I deliberately took a sentence. The tokenizer does tokenization. It does us to have fun with tokens. Somewhat not terribly meaningful sentence, but it illustrates the point that when you tokenize, unlike programming C or Java or something like that, tokenization here is very context aware, and it tries to create the smallest possible vocabulary. So we know that the word token, the ISA word could be the suffix to many, many things, right? To say is a suffix to many words. So instead of having token, tokenizer, token, tokenizer, 4 different words.
Someone on site needs to mute their computer.
Yeah, folks, please mute yourself. Yes.
Yes, so it is.
Who is not mute?
You can also like admin mute from Zoom itself.
I'll
Mute.
check.
Oh, Akira. Okay, I muted her. All right, guys. So can you hear me? No. So instead of breaking it up into using it as 4 different words, it is far better to just have one word token, another word piece either, another word piece s for plural, because s suffix makes the plural of a vast number of words. So you can remove the duplicate simply by having the s suffix. And that's what this does.
Every special character or like apostrophe will also have a different.
Yes, it does, because yes, they also will have their own word in the vocabulary. When you do this, then you tend to have a much smaller vocabulary. The English language has 5 million words, but most of the things can be done. For example, the word uses a vocabulary of only 30,000 tokens. Right? Some tokens are reserved, they're special tokens like the CLS token, the padding, the mask, the separator token, etc. But by and large, they are actually derived from word pieces, word segments. Now, 30,000 is much smaller. You want a smaller vocabulary because when you one hot encode, you don't want to convert a particular word into a 30,000, I mean, 5 million dimensional vector. Especially when you have 512 words, it would be just way, way too computationally wasteful. So you use word segments, and we saw that, right? So for example, here, all the words that end with either. Right? Then we learned about attention masks. We learned about unknown. So then we have a special token for unknown words. So what's the anatomy of a tokenizer? What are the tokenizer itself is a pipeline that's built out of many parts. One is a basic normalization, you know. For example, if you're using a tokenizer like the BERT-based uncased, what it will do, it will convert everything to small letters. It will remove the accents. Then it does something called normalization, which is something I don't understand what it is, but apparently it's done for languages like Japanese and so forth. So that's that. Apparently the same thing can be written in using different characters, and they mean exactly the same thing. Right? So they are literally identical, 2 identical characters for the same thing, same letter. Then we have the pre-tokenization. Think of pre-tokenization as what you would do, for example, in a language like C or Java, when you tokenize a string into words, right? Into sort of break it up onto spaces. Roughly speaking, this is what it maps to, right?
Could you make it a tiny bit bigger?
Tiny bit.
Control plus 1 or twice. Thank you.
Is that better?
One thing is that like in compiler construction, the tokens are being by spaces, right? Over here, the words are also being tokenized, like tokenizer, the token is and iser and s is. So,
yes.
So what's
so you break it up into word piece. So what will happen is normalization. Let's take this. First, the sentence is converted to lowercase, right? And then, you know, if it is a foreign language, remove the accents. All those peculiar accent marks are removed, for example. Then the next thing that is done, so let's say that these 2 things are done. If you have multiple white spaces, they're condensed to a single white space or something like that. Those are basic pre-processing things. Then you do what you think of as programming tokenization, you know, breaking it up on the white space bar or as the boundaries. In the world of natural language processing, you call it pre-tokenization. You break it up into words, but then what will happen is you'll end up with things like tokenization, right? Tokenizer, tokens, all of these words. Then the real tokenizer comes in, the model, the AI model that has been trained kicks in, the BERT model, the tokenizer model. What it does is it looks at all of these words and it has actually figured out what the right pieces should be, word pieces should be. So when it encounters the word, let's say cup, it leaves the word cup alone, right? Because it doesn't see the need to break it up further. But when it comes to a word like tokenizer, it breaks it up into two pieces, token and iser suffix.
Is it like a concept of like a base word, the root word, and then derivative, and then root word
Stemming.
drives like.
Yeah, this question, it's a good question you asked actually. What is this relationship to something called stemming in linguistic processing or NLP? Stemming is that, the root word. Like for example, run, running, and so forth, runner, etc. have the root word. The stem is the word run, and all others are suffixes. Yeah. And there is a close analogy, but not always so. The word pieces are learned. So stemming is linguistically driven. Somebody has sat down and created the stem words, isn't it? A corpus. Some linguist has sat down for that language and created the stem words. Whereas here, the word pieces are learned. Right? The AI model studies the whole corpus of words, right? And thinks.
What's the basis of that learning? Like
The learning
basis of
actually
that
is
learning
pretty
is
simple.
like, it's smart now that it's has token and then iser, right? So
Breaks it up into two. What it does is it looks at the fact that the word segment iser has a pretty high frequency of occurring in the corpus. So it says that because it has a high frequency of occurring in the corpus, it will treat it as a word piece, right? It notices that many words end in S. Therefore, it breaks it out and says, statistically, it's so prevalent, I will consider suffix S as a token. Right? There's no magic. There's no magic. It's just a statistical study of all the words. And figuring out where, if you split, you'll have the smallest possible vocabulary. Go ahead.
What about special characters, symbols, and
Oh, all of them are typically left alone and made tokens in their own right. Question mark, exclamation mark. They're left alone.
so they would have their own.
Yeah, token. They have their own token.
And as we are removing words, how does the output have the concept of as we are removing spaces? Like, how does the output have the concept of spaces? Like,
No, it doesn't. All it is a sequence of tokens. So remember, here's the word. The cow jumped over the moon. The becomes a token. Cow becomes a token. Jump gets broken up into two tokens. Jump token and suffix ed token. Over remains a word, token. The remains a token, of course. Moon remains a token. Let's say that it's like this.
so my question is regarding how does the model differentiate between tokens that have space in between them and tokens just like jump, JUMP is one token, ED is another token.
Oh, because it puts those tokens have a special marker. They are suffix tokens. So very good question. So let's look at this. See. Where am I? So for me, Kate, I apologize. This is too big a font. I'm not able to scroll reasonably. Would this be acceptable, guys? Are you able to read this on your screens?
That's okay.
Okay. Yeah, just to make it a little bit readable. So observe that if you take a sentence, let's take a sentence. The tokenizer does tokenization. It does this to have fun with tokens. I've deliberately created a sentence that has a lot of token variants. So what would you have expected? You would have expected something like this. Without knowing this, think of this as your pre-tokenization step, isn't it? If you were using C or Java, this is what you would get. C, C++, Java, JavaScript, this is what you would get, isn't it? Yeah, Srinath. Yeah. Then what does it do? It first look at the thing. Everything has been converted to small case. Then you notice the token, but you notice that suffixes have a double hash to them. Right? So when you decode it, it will put it back. It will go and sandwich it to the previous word, previous token. Right? That's it. Go ahead.
So in the state, the whole the statement, you have multiple spaces, like the same one if you go up, the tokenizer, the token. If you read that one more time, it has the tokenizer And then after tokenizer does, then the does the tokenization. So the 4 gaps, the
Yeah.
space. So in the entire statement, whatever we have had of one,
There are
so
lots of
all the
white spaces.
spaces is one tokenizer.
No, what the tokenizer does, see, let's
So the
look at
space,
this.
I'm just referring to the space between.
Just the
those two.
space between the words.
Yes.
Yeah. So look back at this picture. First, so think of that statement in your mind. You convert it to a small case. Right. Now think what the pre-tokenizer will do. What the pre-tokenizer will do is it will break up the sentence, the whole text, using, see, boundaries. So you use something like space is a natural boundary. The tokenizer, if you find a space, doesn't matter one or more space, split it.
Yeah.
Right? Treat more than one space as one space and split it. And of course, you don't make spaces into tokens. So the tokenizer
Got it.
remains, right? Then, so those things happen. Now you got it, right? And it will keep doing it. But then at the end, there's a full stop. It turns out that not only space is a breaker, but punctuations are also breakers, because any word ending with cow jumped over the moon dot. So moon dot is not a word. Moon is a word and full stop. The period is a token in its own right. So the pre-tokenizer will take care of that. Then comes the real tokenizer, which will do further mischief by doing word pieces. Right? And then what is the post-tokenizer doing? The post-processing does, notice this. Where was my sentence? Yes, it adds the prefix, the beginner. You know, the special token CLS in the front and the separator at the back. Right. So at the end of it, what do tokenizers produce? They produced token IDs. Right. If you look at it, it produces these token IDs. So I take this sentence. It was Brillig and the Slithy-Toes, the first line of the Jabberwocky poem. Right? By now you must be pretty sure I love Alice in Wonderland and Lewis Carroll and Through the Looking Glass. So this is I love it because it makes sense, and yet it's made up of nonsensical words. Right? So the 101, that's just, you notice that most of the tokens are 4 digits or 5 digits, but 101 and 102, what could they be? 101 is CLS and 102 is the SEP. So what happens, guys, as you become more familiar with all of these models, these things will get imprinted into your memory. You won't forget it.
So I've seen this 3 characters being used for tokens. Is there any specific reason why it's 3?
CLS.
I mean, not CLS, like all the tokens, they're just having 3 character ones, right?
No, not at all. Not at all. Let's look at this. Look at this. I took the sentence to err is human, to forgive divine. Do you notice that some tokens, forgive, for example, is a token in its own right? So the length of a token is arbitrary. And
so you don't split all words.
No, you don't split all words. If a word is sufficiently frequent, as is, it usually prevails. For example, human, you could have done hue and man. Man is a suffix, right? So woman and so forth, but it chooses not to do that.
It's interesting you split for 2 because for and give are different.
For and give are 2 different words. Yes, it did not, partly because when you split on for and give, semantic context is lost. Meaning changes.
So
That's the thing.
as if this only breaks it down, right? So let's say you have in a textbook, a word has to hyphenate to go to the next line. The tokenizer cannot piece back together that word.
Actually, you can do in the pre-tokenization step. So one of the things you do, for example, when you download one of the free books from Gutenberg, right? You notice that it has gone through automated scanning and so forth. So there are a lot of hyphens that are there, right? So there are dehyphenation tools that will dehyphenate it.
So dehyphenation is in pre-tokenizations.
Yeah, you can pre-tokenize. I mean, you can do it. I don't know whether the BERT one has it, but there are tokenizers that will dehyphenate, right? That you can build. So remember that because the tokenizer is God-given to you, or sort of given to you by the people who contributed to the Hugging Face repository, it doesn't mean you have to use it. You can always cook up your own tokenizer. Yeah. Or one simple way is you could prefix the pre-tokenizer with your pre-tokenizer, isn't it? And make it a part of your pipeline. So that's that, guys. Huh? So now, are we all together so far? We're going a little bit slow because I lost some time. So then we did the datasets API. Dataset is a way to, and this is just wetting your recollection. Why do we use the datasets core library in Hugging Face? It makes loading data very, very easy. See, data sets, there are many people have realized that the fuel that feeds AI revolution is data, right? And if you start making data precious and hide it, it is as good as making all your research ideas private, right? Progress happens when researchers share their ideas and share the fruits of their research. You know that, right? In the Western Hemisphere, for example, one of the and people have. So if you look at the fact that why did the West make such tremendous progress, while the rest of the world, the Africa, the Asia, the Americas in those times, with this Native Indians and Australia, they didn't seem to be moving as fast, right? During the whole scientific revolution. There are many causes. One way to look at it is, hey, they pretty much made rapid progress with science, right? And a lot of it. But then why did they make rapid progress with science? Human beings, they have a certain degree of altruism, but that altruism goes only so far as their family and friends, usually. Maybe their community, sometimes a little bit to their nation. People get nationalistic. But generally, altruism doesn't drive progress. Progress happens when human beings find a win-win situation and an activity that is fruitful, economically fruitful. And as a legal expert once explained to me, and I think his view was, it happened, the reason this whole revolution happened in the West is because of a very interesting legal construction. A few legal ideas. First is that the whole world was feudal, owned by kings and queens. And then there was the concept of a corporation, a corp, right? Or traded, a few partners coming together. I believe Denmark or Netherlands, it was pioneered there in those areas. And that's how we have this shared, and it protects you as an entity that protects the individuals participating in a business and so forth. The second big idea that apparently came is that the realization of intellectual property. So a physical property is obvious. This is my land, right? Or my cow, right? Or my table, or whatnot. Yeah. But intellectual property concept, when it came about, it said that people can, when they have some new ideas, they can publish the idea, and they have copyrights to their creative. They write a poem, they have copyrights to the poem. They write a story, they have copyright to the story, right? Copyrights is for any of those activities, and patents are for any implementation of an idea. So suppose you figure out, this is a new protocol. This is a way I can make a hardware, that a chip, a silicon chip, that will, this particular silicon chip will somehow run a transformer head, a tension head much faster than others. Then you can take that to the patent office and say, hey, I want to patent it because it cost me tremendous R&D, and the blueprints will ultimately leak out. Some employee will leak it out onto the web, right? Now, all secrets are ultimately revealed. So I need protection because I've just sunk $1 billion into it. Or here's a pharmaceutical that just designed a molecule, right? So the patent office will give you exclusive right for a certain number of years to the implementation. After that, everybody owns it. So it's a give and take. What do you give? You give you as an inventor give to the world the right to own your invention and use it freely after X number of years. In return, the society, the government gives you protection from copying for X number of years. So it's a win-win situation, isn't it? It's just a digression on intellectual property and copyrights. But ideas are always free. Right? It was very particular that ideas should be shared freely so that they are not continuously reinvented everywhere in a fragmented space and held as secrets. Progress, people realized early on, happens when people don't keep secrets. They share ideas and breakthroughs. Right? So publish it. People will give you heap praise on you or give you credit for the invention, but let progress happen. Right? So ideas are free. In the same spirit, data sets have to be free because data sets are the fuel that runs the AI revolution. So some data sets are proprietary, that's all right, but there has to be a push towards having lots of meaningful data freely available. Then only can we train models and do sensible things. And one of the good things that is happening is they are now entire. For example, Google has a complete search engine just for data sets. I believe datasets at google.com will take you to a search engine that will search the vast repository, the world for online data sets, freely available data sets. US government has mandated a law. If a taxpayer dollar led to activity that created that data set belongs to the public. It must be opened out. So you can go to data.gov and get it. There are entire search engines like this devoted to open data set. Now, Hugging Face in particular has accumulated data sets that you can contribute. You have a data set. If your company allows you to and doesn't feel it's proprietary and must be kept behind the curtains, post it to Hugging Face. Let somebody use it. Kaggle also has a collection of data sets, but Hugging Face also has it. So in Hugging Face data sets, you can use it to get the data set. So this is it. Recap of the last time we did the Hugging Face. And Hugging Face makes it extremely easy to load the data sets. One-liner, right? The emotions data set, here it is. Okay. After the data set, we went to the...
Asif, quick question.
Yes.
Right now, the LLMs are not there yet, but do you anticipate that the LLMs will be able to generate their own data sets in the future?
See,
For vertical, because right now people call data as your moat and hold on to your data so that you can train your LLMs based on that.
yeah, see, at this moment, we are in a very unfortunate...
Sorry to digress from the topic.
No, you are right. It is true that what is happening is, first, people began to hold back the data sets that would train these large language models. And then they altogether started keeping back the models themselves and not contributing. I think this is a really, really bad development that has happened. Somehow the economic model has to be fixed so that these things come back. Ultimately, that these GPTs have been trained on public data. Our writings, our creative work has gone into it. So we do have a part ownership of that. I should have that. So to hold it completely back is perhaps not fair, but the legal system allows it. Some change is needed. Also, what data it was trained on means that you cannot, no researcher can reproduce your work, right? Which is also pretty terrible. And now to your question, can large language models generate data? Large language models are generative. All transformers are generative, right? Well, most transformers can be used for generative purposes. To the extent that they're generative, they can generate data. In fact, they are being used. There's a whole active area of research which says, how do you create representative synthetic data using generative models, using transformers? It's a pretty active field of work. But will we ever come to a day, your final statement, where only the data will be produced by large language models? No. Remember, machine learning always interpolates. Right? So if you have enough points and it can, one simple way to think as a mathematically is, remember I told you that all machine learning models do, for example, in regression, is they discover the embedded submanifold on which data adheres to. The data is proximal to. Training data is proximal to. It discovers the embedded submanifold. But it can't discover an embedded submanifold unless there is training data to begin with. right? But once an embedded submanifold has been constructed, it becomes generative. You can generate infinitely many points by interpolating. Those are interpolations, because the original training data are sort of the linchpins holding the fabric of the submanifold there, right? You can generate it. Will we ever come to a day we won't? That doesn't work, simply because to train the model in the first place, you need real life data. Right? So you can never get rid of real life data. Are we together?
Yes, thank you.
All right, so transformers. Oh, by the way, I hope you guys all got this. We will take a particular library of transformer and use it for classification. The easiest classification task you can think of is sentiment analysis, right? Now, I give you one example in which we did sentiment analysis with 6 sentiments. Now, this time we'll take slightly different. What we'll do is we'll look at, we'll pick a sentiment analysis. Library, I think, image classifier pipeline. Let me just do the graphics. Not images. Right. So the complete pipeline is tokenizer, transformer body, classifier network, right? So this is a picture one of you were asking for. This is the picture, just to recap. Now, we will deliberately go to the Hugging Face repository and pick a sentiment analysis library. Let's see what it does. We pick a particular model. It is bird-based multilingual model. So let us read this word, NLP Town. NLP Town is the creator. Whenever you create a Hugging Face account, you will have a name. That name could be you as a person, or it could be your organization, like Facebook, like NLP Town, like Google, and so forth. Right? It's your organization name quite often. So /bird. Bird is by now, a bird should be as common to you as your own name now. Right? So next time you go to the airport and the cops, the authority asks you, what's your name? Don't blurt out Bert. Go ahead.
Mine already has a name.
Albert, yes. In fact, there is a whole transformer in your order. So typically when models are trained, neural architectures are trained, there are smaller versions and bigger versions. So there's small, base, large, and so forth. So this is the base. What could the word multilingual possibly refer to? That it has been trained on a multilingual corpus. Uncased means all the sentences have been lowercased. And furthermore, it has been tuned on sentiment analysis data. Some form of sentiment analysis data, fine-tuned, right? So let's take that. Let's see how we can load it. You take a checkpoint. So this model name is a checkpoint, right? So somebody has posted a checkpointed model.
So someone took the bird and then bird base and then trained it on multilingual uncased sentiment. This
Exactly, sentiment data. That's what it is. So
we
first,
have four versions of it, kind of.
There is bird base uncased. It just implies that it has been trained on English, not on multilingual. Then there is a bird-based multilingual uncased, right? Which is again trained on generic data. But then it has sentiment just says that somebody has taken a specific corpus of sentiment data and trained it on. Go ahead, Albert.
So you have to name it that way, or it automatically creates the name?
No. You have to name it. And they encourage you. It's just a convention. It's like, when you're writing Python, suppose you import pandas as PD, import numpys as NP, and matplotlib pyplot as PLT. Nothing prevents you from saying import pandas as PLT, import numpys as PD, right? And import pandas as NP. And then everybody will have a tremendous confusion reading your code. Right? It's a convention, right? So you can adhering to the convention is a collective. It's a communal decision, guys. It's a community decision. It's just like what prevents you from driving on the left side of the road, right? We have all agreed to a set of traffic rules, and we don't drive on the left side of the road, at least in the United States, isn't it?
So each model I said, you've already screwed on ahead for the headless, which is where. So for this, I said.
Yeah,
this model is already way
right.
ahead.
Yeah. Yes. We will see that. Hold that thought in your mind, right? So we look at the transformer, but what happens to the transformer? Transformer expects token sequences, right? So what do you need before you feed the text into the transformer? You need a tokenizer. So, and you better get a tokenizer that understands what this expects. So you can't take a tokenizer that produces sequences with special tokens that this model doesn't understand. So a very good idea typically is to take a tokenizer whose checkpoint name is exactly the same, right? Because quite likely it's been done. So we'll do that. You take a tokenizer, and then this is a tokenizer. Download the tokenizer as a model in itself, you download it. And then you take the input. So you take some text. I took a text, which is from Keats' poem. And the poem starts with a sentence, "A thing of beauty is a joy forever." It must be something familiar to you. I took that, and by now you guys must have inferred that I love poetry. Well, that's a separate topic. So you feed that line of poem into this tokenizer, return tensors of type PyTorch. First of all, what do you want it to return? They will return tensors. The two major frameworks are PyTorch and TensorFlow. Right? Pretty much momentum is with PyTorch. There's also a framework called Flax coming up based on the JAX library. But at this moment, it's still immature. So let's look at the output of the tokenizer. I called it inputs. Why did I call it inputs? Shouldn't I have called it outputs?
It's fed into the.
It is the input into the main model, right? That is it. And so there
transfer itself is a model as well.
What's it?
The
Tokenizer.
Tokenizer is a model itself.
Yeah, because it has been trained through AI. So that's it. So now let's look at it. What does a tokenizer model inputs contain? It contains the input IDs, those numbers. It contains the token type IDs. What is the token type ID? Remember, which of the sentences it belongs to, the first or the second? If it is the first sentence for bird, it will have a token ID 0. If it is the second sentence, it will have a token ID 1. And then it has the last attention mask. Means if it has added padding to the sentence, when you do mini batch, we'll see that. But then when you batch, some sentences will be longer than other sentences. So what you do is the shorter sentence, you pad it to the length of the longest sentence by putting padding tokens. But then you don't want the attention heads to start paying attention to the padding. Padding is meaningless, right? So you can prevent it by putting an attention mask, saying don't look there. Right? Just like in Photoshop, you put a mask in an image to focus on only a certain region of the image. That's it. Then let's look at it. Now what happens? Remember, the model needed a pre-processing unit. It also needs a post-processing unit, isn't it? Because it's producing voltages or potentials or energies or logits or hidden state. Pick your name, isn't it? Whichever word. Here I've used the word logits because this model uses the word logits. And by the way, guys, you'll see it from model to model. Somebody will call it logits, somebody will call it hidden states, and so on and so forth. And so a lot of those things will go on. If it doesn't have the word classification at the suffix of it, right, then it will typically just produce hidden states, which can be a huge number. But if it has classification attached to it, then implicitly they are feeding it into, they know how many states, like how many output values are there, how many classes are there in the target space, right? So in this particular case, the target space is rating of 1 star, 2 star, 3 star, 4 star, 5 star. Right? It's called the Likert scale. Right? It turns, a lot of psychologists say that it's the most intuitive scale for people to rate. Right? So 10 is too many, 100 is too much. They won't be able to distinguish if something is, they want to give it 87 star or 88 stars. But 4 and 5 stars, we know. It's a Likert scale. So it seems to be producing it on Likert scale. So that's why it's producing logits. If it was just producing hidden state, arbitrary many, then it would just say hidden states. Typically, it's sort of a convention, guys. So here we go. Logits. But we need to convert the logit into probability, because what does the classifier expect? Probability of it being 1 star or 2 star or 3 or 4 star. So how do you convert logits into probabilities? How do you convert a whole sequence of numbers into probabilities? Softmax. Softmax is a simple way. It amplifies the big guy, makes all the negatives positives, right, and so forth. So we cover that when we do introduction to machine learning. Remember, we'll do softmax and a largest tech function in considerable detail. Go ahead.
So there's 2 stars of inputs. Is that a model name or is that?
Oh, that's a Python way of saying that whenever you give maps or tensors, right, give it like that.
What does no grad mean here?
Oh, very good question. What is no grad? This is something you learn in your deep learning workshop. No grad means the model is already trained. It has 2 purposes. It is to prevent the model from learning even more. Like you're in the inference mode, right? Your model is trained. You're not consciously not training the model on this data. You're just inferring. Whenever you do inference, it's a good idea to do no grad, explicitly to say, do not learn from this data, just give inferences. Because the other advantage of doing that is, so it doesn't tamper with the model. And the second important thing is, when you're in the learning mode, remember, how does learning take place? By computing the gradients and back propagating the gradients. So each node needs to remember not only the output, but it has to have computed the forward output, but it has to also computed the gradients. Hold on to both, right? But that is utilization of memory and computation. So you can prevent, in fact, computing gradients is the more computationally intensive part. The forward is easy, matrix multiplications, and activations.
No back propagation.
No backprop. Exactly. No backprop, no gradients and no backprop.
So like if we go to something like a ChatGPT now, then it would have like, it doesn't learn from it.
Oh, you're in, yeah, exactly. You're in inference mode, unless you explicitly try to fine tune. Now, what happens though is that they are recording all of it, exactly. And they are on their own consciously training it, but you are not doing it. You are in the no grad mode, right? Essentially. So that is the no grad. So guys, is this code now fairly easy to understand? So what are we doing? We got the logits to get the inferences. This line is inference, outputs, right? You take the model, you give it a text, and you say, well, tell me the voltages. Here's the way I think of this, guys, logits. They are bulbs next to the values, 1 star, 2 star, 3 star, 4. What do you want? Whichever is the right rating that this points to, that bulb should burn bright, isn't it? That is the way to think of logits. And you see that the logits that got produced are this. So which bulb is burning bright? 1 star, 2 star, 3 star, 4 star, 5 star. Which one is burning bright? The 5 star is burning bright, isn't it? Now, it is a 5-star rating. Now, if you look at the sentence, would you say that it's a very positive sentence? If somebody buys, let's say, something, let's just say you go to a shop, right? And you see a wonderful piece of craft, and you're so dazzled by it that in great passion you say, a thing of beauty is a joy forever. What is it likely to be? A 5-star, right? So there you go. And so it is a 5-star rating that it produces, right? But then, well, most of us don't think in terms of logits, do we? What do we want? We want it to become a probability, right? next stop in the journey is, for heaven's sake, make it into probability. Which star is it? And how do you do that? That is where you need the classifier head, the softmax head. You pass it through softmax, it becomes probabilities, right? And now let's display it in a more sensible way, like a user-friendly way. So now I reprinted the probabilities by zipping it with the ratings, and I said rating. Yeah. 1, 0 probability up to 2 decimals. I kept up to 2 decimals. And I'm saying that 1% goes to approximately 3 stars. It is pretty clear that it's a 5-star rating, isn't it? Pretty confident. Right. Now, you don't have to pass only one text at a time for inference. Remember, these transformer models, especially when you load them, when this whole pipeline, when you load them into GPUs, right? Into this, right? And when you load them into GPUs, it's inefficient to pass one input at a time. You want to take there's typically a batch size, which is optimal, which will fit into the memory of the GPU. And you want to maximize it because you want the entire multidimensional matrix, right, or tensor to go through its multiplications at one go, right? So you don't have the overload of loading little bits into memory. It is very much like, for example, in the CPU, what do? The locality of references, if you're going to get this variable from the file system, don't just get that variable from the whole page, right? At the same time, between the CPU has a cache, right? It has a cache, L1, L2, L3 cache, and memory is out there. Bank of memory has your data sitting there. But when a CPU hits a variable, it doesn't get just that little bit into the cache. What does it do? Using locality of reference, it gets a whole segment, a page into the cache. Think of it like that you don't want to bring tiny little bits into it. You want to preemptively have entire batches go through it, right? And so that is the technical word is mini batch, but you use the word batch here. People abuse the word and use it just batch. So here's one batch, three pieces of text. Let's ponder over it. If you were to look, what rating would you give A Thing of Beauty is a Joy Forever? Probably 5-star, right? The second one, I would really not recommend this horrible shoe. It hurts on long walks. Bad, right? Then what about this? It's quite satisfactory, but not exceptionally good. Middle of the road. Let's see what happens. Exactly the same code, right? Now, let's see, it produces logits. See, this is the trouble with logits. What's the trouble with logits? It's a little bit indecipherable, isn't it? Unless you're mathematically trained. You keep wondering which is the biggest number here. If you think this looks like the biggest number, actually, no, it is 10 to the minus 3, right? And so on and so forth. So you have to be a little bit careful. So it's better to convert it into probabilities. And when you do that, when you convert it into probabilities, A Thing of Beauty is Joy Forever. The last one has high probability. I would really not recommend this. This has a high probability and it's quite satisfactory. This has the highest probability. Well, let's write it in a more sensible way. This is just aesthetics. By the way, guys, you all have these notebooks now in your. All I did is, how would I convert it into a number? First of all, it produces 5 ratings. I need to know which is the highest rating. Which is the location of the index of the argmax means which index gives me the highest value. And I add 1 to it. Why did I add 1 to that?
It starts with 0.
It starts with 0, exactly. Arrays start with 0 in indexing. Then this is the max. This simply says what was the maximum value. First is where was the maximum value? What was the maximum value, right, for the prediction. So once I get these two, all I need to do is collate it with the text and create a nice little data frame and represent it like this. Right? Which is a little, there's nothing new here. It's just a more intuitive way of displaying this very intimidating tensor, isn't it? It's just a pretty way of putting it this way. So what did we learn from this? What we learned is, let's put together what we learned. you don't, sometimes you get fairly good accuracy because your task happens to coincide with what a model that has been pre-trained has been trained on. Right? Or somebody has even posted a fine-tuned model specifically on your kind of task. That's a lucky day. Yeah. That's when you say in Jabberwocky language, "Oh, frabjous day, Kalukale," if you remember that poem, right? So that's when you go happy. But then all is not done. You still have to use a tokenizer before and a suffix after. And now that is what you would do, except that sometimes what happens is even that is done for you. Hugging Face comes with the pipeline concept. Guess what the pipeline concept does? It does that. If you say sentiment analysis, you can actually say this entire code that we wrote, you could have used the pipeline method and said, okay, here is my checkpoint. And here is use this for the tokenizer, use this for the model, right? Which means that it is exactly identical. It just so happens that the pipeline works for you here. Sometimes it does, sometimes it doesn't. Here in this task it was. So you could have written it alternatively in this way. But the point of doing this was to show how you would go about doing it from scratch, isn't it? Because you would. So remember, we are peeling the onion gradually. First, we just use the pipeline. That's the easiest way to do it. Then we used a pre-trained model because we want to understand the architecture of how these transformers work. So we understood it. And now going forward, we'll do the next step in which we will say, let's use a data set, task-specific data set. Like, let's say that we'll take a task and we say we have some special data. And because your model has been trained on a general data set, like a bird, it's a whole general class of problems, we need to further train it on this task using this data set. Are you getting the point? So then now the last leg of the transfer learning journey that we'll do, right? But before we do it, I'll take a small digression. Now, here is what I would suggest. If you make sure that you pip install the code carbon from a programmatic, this is a little bit you can do, guys. You know, if somebody keeps reminding you that, you know, this is the carbon footprint you're creating, you tend to change your behavior, isn't it? So just pip install the code carbon. And technically, you can do, by the way, you can do this for anything you want, scikit-learn, this, that, anything, any code, especially the code that you run on GPU. Just say tracker.start, tracker.end, emission tracker, and it produces an output like this. So because here I'm not doing anything, it says it will immediately start looking into your system, right? By the way, this was produced before I did a kernel hack to fix it. A platform is blah, right? This is my Linux. It says I have only 125, 120, well, it's 128 GB, but available RAM is 125 GB of RAM. Right, 32 CPU cores and 1 GPU, right, which is 4090. And it says that the carbon footprint was 0 kilowatt hour, right, because I didn't do much. So this, again, this is my little interpretation that transfer learning is the closest we can get to the common concept of the 3 R's: refuse, reuse, recycle. So with that, now the nice thing is Hugging Face, the auto classes, all the auto, this pre-train, etc., it has the code carbon built in. So long as you do pip install code carbon, it will automatically kick in. Right? So all you have to do is on your machine, do a pip install code carbon. And then what happens is it will keep bringing it in, and we'll see it in a moment. Now I'll move a little bit quicker. The other socially responsible thing that matters is, so you realize, guys, I'm showing you the negative side of these large models, AI models. Not negative, but things to be aware of. The other is the existence of social biases. And now, fine-tuning a model. So we know that we can use models that exist. What about fine-tuning it? It turns out that it's a delightfully simple process with Hugging Faces. So we are now going to do the use Hugging Face library to do fine tuning of model. So the 3 core libraries we'll use, actually 2 of them are part of Hugging Face. Evaluate is a separate library in its own, but also with Hugging Face. Data sets, transformers, right? We used it. So we will take, in this, we will take a data set called MRPC. It is part of the GLUE benchmark. In natural language processing, one of the most established benchmarks is called the GLUE benchmark, which is made up of a few tests, sub-benchmarks. One of the data sets used in that is the MRPC. What it has is 2 sentences, and it asks the question, second sentence is a rephrasing of the first, means semantically equivalent, true, false. So it's a classification problem, right? True, false, right? Or if you use a logistic classifier or a softmax, then it is a probability that it is true, right? That it is true. So we'll take that data set. Now, again, the datasets API gives you a simple way to load data. All you have to give it is the name. Here, a pairwise name, because the GLUE contains lots of data sets inside it. You mean specifically GLUE MRPC. You load it, right? You give it the name, and then the data will get loaded. When it gets loaded, you notice that what is the data consisting of? By now, from last session, you know that good data sets have already split the data into 3 parts: the training part, the validation part, and the test part. Right? That's what you would do in scikit-learn, by the way, ML100 or something. You do it by hand, but these data sets, fortunately, are pre-split. But what does the feature set look like? So index we can forget because there's 1, 2, 3, and so forth. The 3 things are there: sentence 1, sentence 2. That from the BART architecture makes total sense, isn't it? 2 sentences go into BERT. Label. Now here the label says what? Label will tell whether sentence 2 is or is not a rephrasing of. Yeah, that is it. 1 or 0. So that is what it is. Data set is, now observe something. The raw data set is not large, right? So can you train a transformer from scratch with just 3,668 rows?
No.
You'll be hopelessly lost. Imagine training a 200, one of these models these days, 200 billion parameter. You don't stand a chance. It's too small. It's too tiny a data set. But you get away with it because you are fine-tuning. You take a model that already understands human language and you fine-tune it for the rephrasing task. You're transfer learning. You take a pre-trained model and you'll fine-tune it on this data set. Are we together? So now, what is the input here? Sentence 1, sentence 2, output is a rephrasing or not? Yeah, isn't it? Now we load so this is the BERT. If you remember, we did the BERT research paper. Now there is one more beast we need to introduce into our zoo. And this beast is something called data collator. Now, what are data collators? See, what happens, as I mentioned, when you send data into a transformer or into a language model, you don't want to send one at a time. You don't want to trickle feed drop by drop and say, what's your inference? What do you want to do? You want to send batches of data. But when you send batches of data, sentences, human sentences have arbitrary sequence lengths, isn't it? So what will happen is the whole thing won't look like a tensor. Tensors are boxes like this, right? Like a book. You don't have books of, like, imagine reading a book in which each page was of a different size. You can have a notebook like that. Human beings can write on that, but a printer will not be able to print on such a book, isn't it? In the same way, you need to make sure that all the sentences that go into the, or rather the token sequences that go into the transformer are of the same length. So what do you have to do for the batch? You will have to pad it as needed. So Sometimes you need, sometimes you don't need padding. Huh? So padding is one of the things a collator may do. The other thing, but the main thing that a data collator does is you have this entire data set, 3668 instances of data. You can't feed all of it into the transformer. That is one extreme. You don't have that memory. You don't want to feed only one at a time. That's the other extreme. You want to send it as mini batches, right? Or people just colloquially call it batches. So you choose a batch size. Now, what the collator does is exactly that. It will automatically break up your data and feed it into the trainer batch by batch, right? I call it, so here is maybe a metaphor that you may, that may help you. Imagine that you have you wanted to do something in your backyard. So somebody has come and dropped a truckload of sand in your front yard, right? And you need to take it to the back and use it for whatever garden construction work you're doing. So you don't want to take one grain at a time. That would be rather inefficient. But you want to take buckets at a time. That's one batch of sand for a purpose, because that's more efficient. But you can't take the entire truckload on your either, right? So collator will do that for you. So what is the journey? This is your journey. The dataset loader loads the data. Of course, you remember we use the dataset loader to load the data. Then you use the tokenizer to do is pre-tokenization, normalization, actual tokenization, post-processing of the tokenizer, but the tokenization, roughly speaking, to do all of those things. So now it has become sequences of tokens, 2 sequences of tokens, one for the first sentence, one for the second sentence. That's your input. So you have a huge pile of them, pile of these pairs. But now imagine bucketfuls of them have to go into the model, right? So who is going to bucketize all this? Who is going to divide it into the batches? It's the data collator. And while it is doing it, you can ask it to do some extra things also, add paddings for this purpose. No, add padding. So that's what it does. That makes sense, guys? So this is it from now. This is the rest of it. This is very easy. What happens is that you have this entire data set and you want to transform the data set sentences into tokens. So you need a function that can do that. What is that function? The tokenizer, of course. You need to treat it as a function. So what you do is you create a little function, given an example, which will be a pair of sentences. You feed it into a tokenizer and it will do that. Now, the only thing worth noticing here is that till now, we have been to the tokenizer, we have been feeding in one sentence, but here we are feeding in 2. That is okay. Any BERT-aware tokenizer can take 2, right? And so it is fine. It will return you 2 pairs, 2 sequences in return, right? And so it will do that. So you take the raw data set and you transform it using the map function, map as in map reduce, thinking in programming, give it a function. It's a mapping function, and it will return you for each element. It will return you the tokenized version of that element. And now what do? You create a data collator with padding and you give it the tokenizer so that everything can happen properly. And after that, it's easy. Go get a pre-trained model. We take a pre-trained model. And now comes the interesting part, right? The interesting part, and by the way, this warning is worth reading. It says some weights of the model were not used when initializing BERT for sequence classifier. So certain weights were not used because this is expected. This is expected because you took a model meant for trained on something else, and you are using it for this purpose, so that certain things have to be ignored. Right. So now let's look at the trainer API, which is the heart of it, which is actually, those of you who have taken the deep learning course with me before, and the PyTorch loop, where you have to hand out the entire training loop for every epoch, for every mini batch in the epoch, run the forward loop, forward process, then do the backward to compute the gradients, right? Then back propagate the gradient, everything. Then you had to do all of that yourself. You don't have to. It makes it easy. It internally does all that, guys. And that's all. It's nothing fancy, but it is still a convenience that to the trainer constructor, you can give it the model. You can give it some training arguments, think of it as configuration. What are the training arguments we use here? Just simple give the name of a trainer. So what it will do is, see, when it trains, it produces a model, right? It needs to store the model somewhere. What it will do is the test trainer will become the directory, subdirectory in your, wherever you fire it off. It will create a subdirectory and store the checkpoint as a model by this name. Right? But don't upload it to Hugging Face calling it test trainer, because nobody will know what test trainer is. Right? So this is it. Now you have a training set, you have the evaluation set. Why don't you have a test set? Why do we not pass a test set? It wouldn't make sense. When you train a model, the last thing it should be aware of is the test data, because that would be the leak. That's a holdout. Yeah, that is the absolute one thing the training process should never ever heard of. You hide it under the pillow and say it doesn't exist. Right. So that's the thing. Collated. So this line of code, guys, is it pretty much self-evident? Right, the constructor.
Can you make the test trainer, like what was your point on that one?
See, what happens is that there are three things. You train a model, but because it has hyperparameters, you'll have to figure out what is the best hyperparameter. So you change the hyperparameters, but the thing is that what do you test it on? You create an evaluation set. You keep testing on that, how well it is doing. So to the AI, to this process of cross-validation, the evaluation data set acts as the test data set. It never really sees the real test data set. Because if it sees that, it will start learning from that. Right? It has to do, this is the boundary. It should never ever come to know about the test data. Because then only whatever hyperparameter tuned cross-validated model that you have, that you'll apply to the test. And that will give you the true model performance. You never learn it, because the cheating is when you say, okay, let me tune the hyperparameter so that it does well on the test data. That is wrong. Right? So this is it. Guys, run it on your machine. On my machine, it ran in 33 seconds. Right. See how long it takes. Now, when we run it, obviously the training loss decreased, but then comes one more thing, the evaluate library. It also is very much like, see, these data sets tell you what is a sensible evaluation metric, right? So for this, a paraphrasing problem, obviously accuracy, right? It's a binary classification problem. So when you have a binary classification problem, what are the metrics? Accuracy, precision, recall, F1 score. Now here, paraphrasing or not, it's hard to tell what's a positive, what's a negative. So let's take F1, which is the harmonic mean of the two. So you take that precision and accuracy and F1 score, something like, so it will tell that you can use that. And all that you do when you compute the metrics, what do you need? You need the predictions, the Y hat and the Y. Remember, in the language of machine learning, Y hats and the Y, the predictions and the ground truth. You'll compare those two. Here it will say it is a paraphrasing. Oops, the real answer was it is not a paraphrasing. Error, right? So that way. So you use that. And after that, the trainer just needs to be trained. It's very one-liner to train it. And when you train it, you get a result like this. Again, about 33 seconds. Try it on your laptop. So this is the work you'll do, guys. Now, we will take, it is time for lunch. You have the usual, it is 1 o'clock. You have 2 hours. We'll have 5 minutes for QA, then the usual time, 2 hours. What will you do in 2 hours? 1 hour for lunch, 1 hour for
Labs.
Labs. Do the labs and then come back. If it doesn't, take help from us and from each other and so forth. Right? Run it on your machine. If you have headaches, then stop us. And the thing is, guys, absorb it. Make sure that you're not just blindly running it. Every line of code, if you don't understand it. Now, I'll give you a homework. This is the lab. There's a homework beyond this class. we have done it on a paraphrasing data set. Do the fine tuning. There is an emotions data set. Remember the 6 emotions? Now take a binary classifier, take a simple pre-trained classifier, not a binary, just a pre-trained classifier, right? Transformer model, and make it work on the emotion, fine tune it on the emotion data set and see how much your model performance improves. Are we together, guys? What I said, there is an emotion data set there. Your homework is to fine tune a classifier on the emotion data set and then report the model metrics. Please do that. Please do that. That is your work. If you can do it in the lunch hour, and by the way, it's possible. With luck, you can finish it in an hour. If you can't do it later on, after the class is over.
Can you repeat it again?
See, we used a classifier to do this.
Yes.
Now use the classifier for another thing, sentiment analysis. Fine tune a sentiment analysis using the emotion data set. Remember, emotion data set means the 6 emotions. Fine. And then report the model metrics, like what is the accuracy, what is the F1 score, right? Are we to do that? That is your longer homework. And guys, just follow this pattern. If you follow, the hint is, if you understand this notebook, you realize that it's exactly the same thing with minor changes. But then you should be able to transport or transfer your learning to another problem. Right? So do that, guys, and we'll take the break accordingly, run it on your laptops.
So the answers that you're expecting.
Today morning, we did a series of labs. We finally ended the journey with a complete transfer learning. We worked with some pre-trained models. We learned about tokenizers, pre-trained tokenizers, and then we learned how we could use our data set to fine-tune a model for our specific task. Right? So that concludes the pretty much what you do these days to solve most of the problems. Most, but not all. There are problems for which you will have to think of new neural architectures or new algorithms and so forth. In fact, the fun of this field is that you hit issues in which the state of the art is not good enough. And you have to sit and think, what do I do? You can go some distance by doing all sorts of hyperparameter tuning and neural architecture search. But even beyond that, quite often, you have to go back to the books. You have to go back to the math and think of something new. And that's where the fun begins. In fact, you create many, every week you see a crop of new algos, new architectures, new things coming up. The field is moving very fast. The fact that people are creating new models, new algos, speaks to the fact that the state of the art in many areas is not good enough. And people have a need to create this. Isn't it? So actually, this was very interesting. Just yesterday night, I noticed that a very well-respected author, he said that actually the real work is in systems engineering, right? Of machine learning pipelines, you know, the data mine and all of the pipeline. The actual training of an AI model is the easiest task. Yeah. I sort of disagreed and I posted an opinion there on LinkedIn. See, every work is difficult, but if somebody has done one part of your work for you, or it so happens that your task is easy, then the other parts look difficult, right? They remain relatively harder, but it's not generalizable. You can't trivialize the hard work that goes into thinking of new AI models or new machine learning algos and things like that. So don't do that. So anyway, that was the lesson from the morning. The second lesson is, despite the fact that fine-tuning is a last mile journey, nonetheless, your laptops and the time it took to train these models on your laptop, it speaks to the fact that that itself is very time consuming. Most of you took between half an hour to 1 hour, isn't it? To train, to fine-tune this model, to run a few epochs. In fact, just 3 epochs over this model. Now, one thing you notice that by the time the first epoch finishes, already most of the accuracy or F1 score is achieved, isn't it, in the first? Then loss function stabilizes and so forth. You never know how many epochs are needed, right? After a certain number of epochs, and you learn in deep learning, the curve flattens. You reach a point of diminishing returns. In fact, not only diminishing, nothing happens. It's literally flat, 0 returns, because all you're doing is you're just moving the weights, perturbing the weights a little bit, and more or less keeping it the same. So it is very hard to know a priori how many epochs will do the trick, right? But the rule is you continue that, but what people do is early stop. Once they notice that epoch after epoch after epoch, you just keep checkpointing the model. And after they notice that they started off with, let's say, 20 epochs, but let's say by 5th epoch, they notice a flattening out, they'll stop early, right? They'll stop the training early because they're done, right? They don't want it to overfit. So that is that. So if fine-tuning the last mile journey is this time consuming, you can only imagine what the main pre-training journey is like. The journey more like a journey of 1,000 miles there, right? So typically it takes something like anywhere between 256 to 512 to 1,000 servers, weeks or months of continuous running, of training, before one of these models are born. It should give you an idea of how these things happen. So that brings us to the topic that is now. I hope you guys are seeing my screen. The idea goes to the idea has been around since 2006, but it sort of gained attention once Jeffrey Hinton, pretty much the father of this field, wrote an interesting paper in 2015, which is called distillation loss or distillation learning. The idea was, and this idea obviously predates him. The concept predates him, but he came up with a nice way of formulating it. I believe it goes back to 2006 at least. The idea is this. Suppose you have a big model. Now, I will put it in ways that is geometric, and I haven't seen anyone else put it like this, but I like to think of it like this. See, what does machine learning really do? What are those weights ultimately saying? Those weights are, so suppose there were only 2 weights, one bias, one weight. It is the equation of a straight line, isn't it? What does it do? When you make a prediction using the in the parameter space, in the weights and biases space, or what I call the hypothesis space, it is basically different representations of loss, and they form a loss surface, isn't it? The correct weight and bias is the minima there, right? Now, in real world, that represents a straight line of regression. If you have 2 weights and a bias, it represents a plane. Now you can generalize it. So you could say that when you have a whole lot of weights and biases, at the end of the day, what is representing is in a very, very, very high dimensional space. It is some input space. It represents regression. Let's say that the problem is regression. Then it represents some hypersurface to which the data is close, sitting upon, right? Practically sitting upon it, slightly bouncing up off it, right? The way raindrops sort of bounce off the water, sort of around that. Another way, if it is a classification problem, then that hypersurface is the decision boundary that separates out, let's say, the cats from the dogs, isn't it? That's another way of looking at it. But at the end of it, the way I look at it is, what these models learn is a very complicated hypersurface. You ask this question. Okay. Go. Okay. So now the question is, how do you train it? So a little bit back to the basics. And this idea is very interesting, guys, because these concepts go beyond just this distill bird. Huh? So I want you to, obviously we'll do it in deep learning in a much greater way, but I want to try and explain it in this time.
Yeah, Asif, can you re-explain? I did not get much of what you said earlier.
Okay, there are 2 ways of saying it. One is go register for deep learning. You'll learn it in a slow and nicer way. But the other way is, I'll put it this way. So both for you, Kazi, and for Mosmi, what it is the problems of regression and classification. Let's take these two classic problems of supervised learning. One way to look at it is if you build a model. So for one moment, just forget deep learning, right? Just think linear regression, right? And you take linear regression, right? And what are you doing? Suppose there is one input, one output. Not even linear, just regression. So linear regression would say, what is the best fit line between input and output? It's a straight line. Now you make the line flexible. So this is very rigid. You make it flexible. Go to polynomial regression, various kinds of regressions. At the end of the day, it is the search for the best fit curve. Another way to thinking about what is the best fit curve? A curve is a function mathematically, isn't it? And therefore, regression is the search for that function that best gives the relationship between input and the response. That is easy, right? And now generalize it to two input variables. That curve now becomes a surface, right? X, Y, Z, it's a surface. That gives you the real data points. Now this surface will not go through every point, but it will be sort of close to it. And now you go to 3 dimensions, it becomes a hypersurface, isn't it? So you can say that for regression, it is the search for that hypersurface that best fits the data, because it's the search for the function. What are you looking for? You're looking for that approximator function. Yeah, you will never know how the data was generated, because it's a Sherlock Holmes problem that we solve in AI, machine learning. People don't tell you what the function is, because if you know it, there's no reason to build models. But because you don't know what the generative function really was, you're trying to approximate it with any function that works, that fits the data. Yeah. And it turns out that it is good enough. You don't need to know the real function, because within the domain, the two may be equivalent up to very small variations. Now, so now if you think, and classification is what? It's a search for a decision boundary. Mosmi, are we getting it?
Sort of, yes, please continue.
Yeah. Okay, so we'll do all of these things in greater detail, Mosmi. Yeah? So like, for example, in a certain space, let's say XY space, okay, let's take it this way. You have a certain weight, a BMI, right? And you have a certain A1C sugar value. You would agree that up to a normalization, once you normalize the data, the healthy people will be close to, well, let's just say in a ring, the BMI will be in a healthy zone, and sort of the weight, yeah, would also be in a, I mean, A1C would be in a relatively healthy zone, right? So they sort of form a ring, a kind of a structure, and they sort of go together. Well, I don't know if it is, but okay, some region in which it is good, and other regions in which it is bad, right? So let us oversimplify the problem. Let's say that being featherweight is not a problem, being malnourished is not a problem, and A1C going down to 0 is not a problem. Then the only boundary is the high A1C and the high this. So what can you do? You can take people's BMI and plot it on paper, and what you will see is a gradual decision boundary will emerge between the healthy and the unhealthy people. Unhealthy people will tend to have high BMI, high A1C, right? And closer to the origin in the quadrant will be that. So you can draw a decision boundary. What's a decision boundary? It's a curve. In higher dimension, it's a surface. 2 dimensions, it's a surface. 3 dimensions, it's a surface. In 4 dimension onwards, it's a hypersurface, right? And classification is nothing but the search for the decision surface or decision hypersurface. That's what I was saying. Now you got it, right? So this is all basic geometry. And now take this idea further and say that, and a little bit hand waving, but let's say that you built a model. Here is a model that has this very complicated surface that fits the data. Let's say that it's a regression problem. I'll take as an example. Now the question is, it's making very good predictions on the data, right? But can we have a simpler model? There are two ways of asking this question. The way this model has been trained, so you can imagine that if you just look at this thing, right? If you have a very complicated surface, you can have a smoothed out surface, right? Can you imagine? With a little bit more smoothed out, how should I say? So, when you look at the mountain from a distance, you don't see every little bump. It's a little smoothed out approximation of the surface, isn't it? So now, if you try to learn a smoothed out surface, you're deliberately not trying to necessarily capture all the nuances. So you are willing to trade off a little bit of accuracy. But the question is, can you get away with a much smaller model? Right? And that is the idea. Geometrically, that's the idea. So now let's ask ourselves, how would we do that? And this is where the trick is. This is the main intuition, guys, of distillate learning. See, the bigger model, which we'll call the teacher model, right? With all its grand bells and whistles and ability to flex its muscles like this, what does it do? It sees vast amounts of data and it says no problem. And it goes and builds this very complicated, bumpy surface out there, right? Now, despite its fitting, you know that the real data will not be just sitting on the surface. There will be residual errors. There'll be, some of them may be sitting, but most of them will be off. And sometimes the error will be large. That is what the residual error is, right? Mean squared error is. So the squared error is. They'll be all over the place. You try to minimize the mean squared error, that's all right. But basically, that's your loss. But ultimately, there will be loss. If nothing else, there's irreducible error. They are that. Now you ask yourself, what should the student model do? Now, traditionally, you would say, hey, let me try a smaller model and fit it also to the data. And maybe it will come up with a not so complicated surface, right? But lose some accuracy. Then what would you do? You would train it against the real data, a smaller model. But the key insight here is don't do that. For the simpler model, what you do is you don't try to catch up to reality or compare it to reality while training. You instead compare it to the prediction of the teacher, right? So you don't say learn reality, right? You say learn the great teachings of this Ustad or this Guruji, right? Whatever he says is right, kind of thing.
So like in Google, I think there's some article about one of the engineers left, like the ML scientist or something, and he was complaining that these guys are asking him to like use the ChatGPT model to train the Google model.
Okay, possible. That's a student-teacher.
That's a
teacher
student
student. Yeah.
Isn't it what Stanford did for
Alpaca.
Alpaca?
Yes. So this approach is a dominant. Once you get used to it, you will realize that you get jaundiced eyes. You see everybody has been using it, and also you see lots of opportunities to use it. Right. So think about this way. Look at it this way. Why will a smaller model work? There's a complex reality. But however complex reality, the bigger model, the teacher model, has still created a hypersurface which is not perfect, because the reality comes with the irreducible errors and many things that your data doesn't know, right? So it is itself an approximator. Remember, neural networks are universal approximators. So it has come up with all its bumps, it is still a smoothing out on the reality. So a smaller model is not trying to learn the reality whose complexity remains invariant. It is trying to learn a lesser than reality model, right? It is trying to learn from the predictions of the teacher, right? It's saying, hey, teacher, for this input, what would you predict? And now I'll predict something and see what happens. And I will try to converge the gap between myself and the teacher. So if I can become the teacher, right? For all practical purposes, barring 2-3%. Hey, pretty good, right? Pretty good. No, so for example, if you're learning from Shakespeare, you don't need to be Shakespeare, right? Even if you come within 2-3%, you'll still be world famous as a poet, right? I'm told that at one time, a lot of poets, it was de rigueur to learn the style of Shakespeare. But methinks thou dost protest too much. What was that? It's a Macbeth, I believe, right? Macbeth, yeah.
This small model, right, whenever the
Mhm.
student comes, it will have like either more residual errors also, right? Because if the residual errors were on the master.
Yes, that is true. It will have. But the idea is, how much more? And the beautiful thing that will emerge as I take you through the mathematics is, you realize, you know what, not much. Right? And this is unexpected. In fact, this was the main idea when the discovery. So distillation is a mathematical discovery that you can do that. And I'll explain it to you, but I'll explain it to you ab initio, means from first principles, if that is all right. Huh? So bear with me, guys. And if your mind is not fresh, take a 2-minute break to jump around a little bit, freshen yourself up, and sit down, seriously, because I'm going to go in a mathematical journey.
So is there a right way to get the correct prompts from the Guru model so that we can train the...
That's exactly what we'll learn. Hold on to your thought. Hold on to your thought.
So, is it Jeffrey Hinton?
Jeffrey
The
Hinton,
paper he wrote that?
yeah,
So,
2015
so
paper.
as a metaphor, that's like, if you want to descend down a mountain without snow, you're going through all the cracks down.
That's right.
But a distilled version would be like with your snow,
Yeah.
You flatten out some of the ridges, and
That's
it's
right.
still the same way in descending.
Yeah. Actually, Patrick gave a very good analogy. He says that if you have a mountain, it has a lot of little bumps and cracks and things like that. But when it snows, it becomes a more smoothed out version of the mountain. That's an excellent analogy, right? That's an excellent analogy. Very, very good. All right, guys. So I'm serious when I say freshen yourself up, because this intellectual journey, I think you'll enjoy. Yeah.
What's that word you were saying, like from first principles to Latin?
Ab initio. It's a Latin.
How do you spell it?
Patrick will tell you. So I'll go back to the principle by asking you, do we understand what probability is? So it turns out that, and of course, if you go to the probability has two possible interpretations, the frequentialist and the Bayesian. Right? But we won't go too much into it. One frequentialists say the simpler version is, if I go on tossing a coin and do infinitely many trials, then the proportion of times it is head is the probability of a head. Right? The crucial word is long trials or infinitely many trials. The trouble is, in many real life situations, you don't get to do many trials. So for example, what is the probability that if we continue our human activities as it is, we'll end up with an environmental catastrophe, right? We'll end up with the extinction event. The problem is you don't get to boil the earth 1,000,000 times and see how many times it caused extinction, isn't it? One time is too many. You don't want to risk it. So, and yet we speak meaningfully about probability. So, and this is, by the way, if you look at the people who are climate change deniers, they keep pointing this out. They say, where is the data, right, showing that we are causing global warming, right? The thing. I think at the end of it, when you distillate all of that, it boils down, if you really parse their argument carefully, it boils down to the fact that they're taking a frequentialist way of thinking. They're saying, have you actually had 1,000,000 runs of people screwing up the planet and seen how many times it led to extinction? Right? You don't have. So stop making theories up. Right? All the scientists are just cooking up. It's a conspiracy. They're cooking up theories. Right? But there's another definition of probability, which is the Bayesian definition. It's a digression, by the way, that I'm mentioning it. The Bayesian says the degree of doubt or the degree of belief. So it takes an approach and it says that probability is a measure of to what degree you believe. You say, well, to what degree I believe? How can that be? Probability has its very rigid math. Probability of two independent events happening is the sum of them. If they can happen, blah blah blah. You know, A plus B. All of these rules of probability. It turns out that if you look at degrees of belief, it follows the same arithmetic. Now, here's the interesting thing. What it says is that data takes you from a prior belief to a posterior belief. Right. So what does it mean? Let's say that I believe that there are two hypotheses. The earth is a sphere, right? Or the earth is a pancake. Right. Now, I have no data. So I can believe half and half. Let's say that I strongly believe that the earth is a pancake. I may even say that I'm 90% sure, 100% sure. Well, never be 100% sure, but let's say 90% sure that it's a pancake. Right. Now, you have data. You keep going in a straight line, right? And you don't meet the end of the earth, and you don't meet the end of the earth, right? And after a little while, it seems that a lifetime may go by and you may not meet the end of the earth. And by the way, that hill begins to look like something I encountered a few months ago, right? Even though I'm going in a straight line. So now what is this data doing to you? Belief. It is diminishing your belief that we live on a pancake, isn't it? And it is increasing the belief that you live on a sphere. So this is a Bayesian way of reasoning. And all of science is Bayesian thinking. Science makes the position that you can, in the beginning, believe whatever you want, doesn't matter, right? But so long as you're willing to refactor your belief, once you see the evidence, you let evidence change your belief. Right? So start from anywhere, doesn't matter. You'll come to the same answer with sufficient data. Right? So that's a way of thinking. So anyway, that is the probability. But with these two definitions, I won't squabble over them. I'm mentioning it because it's worth knowing that there are two ways of looking at reality. Right? And also because in schools, they always tell you the frequentialist definition, which in my view is actually not the preferred way it should be. It should be the Bayesian way. Right? So now, suppose the reality is that it's sunny and you have a prediction model. Your weatherman, has it ever happened that your weatherman says it's going to be sunny and it is sunny? Sometimes it happens, but sometimes your weatherman says it's going to be sunny and you're unpleasantly surprised in the rain. It rains on top of you. So now here's the thing. Suppose he said the probability of rain was 1%. And you went out. So he's basically saying it's going to be sunny. You went out and it rained on you. Are you surprised? You are surprised. On the other hand, if he said 99% chance it's going to rain, then are you surprised? Not so surprised, right? So we will create a construction process. I'll just take you through this. Surprise. Oh, sorry. We'll create a mathematical formulation of it. It seems that it is the reciprocal of probability. Considering that something has happened, if your model predicts the probability of its happening as P, then this. So for example, 1%, P is equal to 0.01, then surprise is 100, right? Approximately 100. If P is equal to, so 1 over P is equal to this. If P is equal to 0.9, right? 1 over P is 10 over 9, right? How much is a surprise? Approximately 1. Isn't it? So now that begins to look like a good way of quantifying surprise, except that this way of quantifying it has one minor, one thing that gets the mathematicians into a knot. They say, well, you know, there should be no surprise. If there's a 100% chance, model says 100% this will happen and it happens, where is the surprise? There should be 0. So how do you take something that goes from 1 to infinity and convert it into something that goes from 0 to infinity. Take the log of it, right? If you take there's one way of doing it. There are many, I'm sure there are arbitrary many ways of doing it. So let me put it this way. So surprise, right? So let's just say surprise attempt 1. Or V1 release, V1 beta, or something like that. Release of your formula for surprise, 1 over P. After a little while, you realize that you can have a better version, new release, right? V2 release. This is log 1 over P. Right? Happening. And now let's take this. Suppose you're training a model, a binary classifier, right? And the binary classifier's job is to pick it. Is it a cat or not a cat? Right? So you would agree that when it is a cat, let's say that when it is really a cat, right? You add up all the points where it was a cat, and you sum this up. This will be a total surprise, right? And for all those situations when it was not a cat, right, it was a dog, let's say, it would be log 1 over. So suppose it was a dog and you said the probability of a cat was 0.0001. Probability of a dog is high. There's no surprise, isn't it? So it would be a 1 minus PJ, right? Situations where dog, cat. Would you agree? This is your total surprise, right? Am I making sense, guys? Yes. It's pretty easy, right? And now suppose I insert I say the label y for cat is equal to 1, for dog is equal to 0. Now this is the total surprise. If I multiply it by the label also, I can say cat and a dog. Right. Well, dog is 0, then this whole second term will cancel out. You don't want that. So what you do is you multiply it by 1 minus dog, the label for dog, right? So which is the same as saying this is a y hat, y log. Well, okay, let me not get into the exact terminology, and let me just for the time being stick to this. So right, this is the label. This is the actual reality. Cat y is the label, right? 1, 0 in a machine learning model, label. And what is your y hat? What is the prediction? Prediction is a yi, given y. The prediction is just the probability, isn't it? So putting it in more traditional language, you would write it as 1 over yi hat. Would you write it like this? Right. A plus cross and j 1 minus like yj, the negative case, right? Log. This is just a mathematical way of putting it yj. No, but ignore it. I'm trying to, if this math is looking puzzling, I hope you agree that if I just sum up all the surprises, let's keep it very simple to the really meat of the matter. 1 over pi, or the prediction, which is the same as 1 over yi, which is the same as, now log of 1 over something is negative log of that. Hat, prediction, right? Yi hat, the predicted value. Would you agree? This is the net surprise for only the positive case, for example. Would you agree, guys? Right? This is a total surprise. Actually, so when you train your neural network or whatever classifier it is, all you need to do is there should be the least possible surprises. Its prediction should match reality. Would you agree or not? Isn't it?
Does the 1 minus dog, should, if that's supposed to be dog, isn't it just 1 minus cat? You define both in terms of cat.
Right, that's right. And so the other term, the other term here is 1 minus, like 1 minus, yeah. So like yi. So what people do is they minus summation over log 1 minus yj for the dog. So this is for the dogs, which is the positive case cat. This is for the cats, and this is for the dogs.
Okay.
No surprises for that. Both the terms are it. Cat, dog, not cat. Dog is not cat. That's about it. Right? You would agree, right? That if it is a probability of a j, let me just use j here, the second notation. So what do you want? If it is a cat, you want the probability to be as high as possible. If it is a dog, you want your model to predict the probability that it's a cat to be very, very low. Isn't it? Means 1 minus that probability should be high. That's it. So this is called, believe it or not, this total surprise is, what is it? Have you encountered this formula anywhere? This is literally goes by a very fancy name, cross entropy loss. Right? It is the loss function for classifiers. Right? Yeah. Now, I gave you an intuitive explanation for it, and suppose you're as a mathematician, you're frowning on me, and you are very unhappy. Let me assure you that this is valid. You can use a maximum likelihood estimator argument and rigorously prove this, MLE. Right? So, and we will do that in the ML100 course. Those of you who are registering for it, we'll go through the derivation. But suffice this for now. So see, what happens is, this we now know is the loss function. Loss function is, right, that you take the, so suppose you take the cat is equal to 1, right? So the loss function in a fancier way is to say yi, because yi for cat is equal to 1, so 1 I can prefix. It's just a fancy way of writing. There's nothing very special about it, like this, minus loss is equal to this, minus again 1 minus yj, cat, dog, 1 minus yj. For dogs, log yj hat. Oh, 1 minus yj hat, sorry. Now, this is basically 1 and this is basically 1. You know it, right? If you call cat as 1 and dog is 0, then 1 minus 0 would be 1 also. This is your loss function. And when you train a classifier, you try to minimize the loss. Very intuitive way of saying, let's build a model that surprises us the least. Would you agree that that is common sense writ large, isn't it? So it's one of those things, guys, when you look at the mathematics and you really think about it on your own, you will realize that it's saying something absolutely common sense. Now comes the question of the student and the teacher, right? So we will come to that. But before we come to that, I will take a small mathematical digression into something called softmax. Right now, softmax is an interesting term, and many people have argued it should have been called soft argmax. Right? So what does it mean? I'll keep it brief because in the theory sections we'll do it. So remember that some model, whether it's a whatever model it is, has produced some energies, some logits, right? Voltages or potentials. Now you need to convert it into a probability. One easy way that you could do it is add up all of those numbers and divide each number by that. So each number will become a fraction. And you can say, well, that's the probability. There are two problems with it. You'll end up with negative numbers, right? Because what happens is minus 10 is divided by whatever you divide it by. It will be that. And the second thing is, if the addition of all those numbers is very small or close to 0, or your probabilities, even the positive ones, will be beyond 1. So they won't be constrained in the 0 to 1 interval. So you say, well, that's not good. Let's do one thing. Let's first convert everything to positive numbers. Right? So one way to convert a number line from minus infinity to plus infinity to be constrained to 0 to infinity is the opposite trick of what we just did, log. anti-log. When you exponentiate a bunch of numbers, what is the exponentiation of e to the minus infinity? It is 1 over e to the infinity. And so it is 0, nothing. 1 over an infinitely big number is 0. On the other hand, positive numbers will remain positive, isn't it? So negative e to the minus negatives will give you a number between 0 and 1, right? Because the hard lower bound is 0. And positive numbers will give you value above 1, and they'll keep on. So that is one problem solved. But now there's a beautiful thing. All the numbers are positive, they're additive. So surely the sum will be more than any one of the numbers, isn't it? And so now you take the proportion, they'll become probabilities. Do you see how simple the idea is, guys? Common sense, right? And to do so goes by the fancy word softmax. Right? Let's do this example. Suppose you get the potential -2, 1, 3, 5. Right? Now you realize that actually, let me just make it this way. -1, -3, 3, and 1, 2. Let me take it like this. Right? Now, guys, what is the sum? Sigma is equal to 0. Terrible. You can't do probabilities with that. Now you'll have minus infinity and plus infinity. That's all you'll get. So that won't do. But when you exponentiate e to the -2, e to the -1, e to the 1, e to the e square. Now let's see what these come out to be. Want to try it out? Right. Let's see. 1 over e square is approximately 2.7. 2.7 square should be about 8. Can somebody do it and see? E square is approximately 8. Right? And 1/8 is 0.16. And this would be 1.3. Approximately, let's give or take. So I'm using approximation, mental mathematics.
0.14.
Yeah, and 8. So guys, observe these numbers carefully. What do you notice? First of all, they're all positive, right? Also notice that 2 was only twice as big as 1. The biggest number was only twice as big, isn't it, guys? As the second biggest number. But once you exponentiate, what happens? Yeah, it becomes almost 3 times, right? So what does the exponentiation do? It exaggerates the large relative to the next large, isn't it? And here comes Jeffrey Hinton's key insight. I want you to just keep staring at it and think, what could be, what 8 tells is good. Now, when you make it into a probability, so if you add it up, well, it all adds up to 8, 11. Let's say they all add up to approximately 11. 8 over 11 is 0.777 or something like that, 77% probability, right? 25% probability. Am I right? By the way, mental mathematics, anyone? I'm just hand waving math in my head. Anybody could verify this? Right. So when you divide it by adding up 8, 10, 11, let me just say 11, approximately 11, what you will get is practically 0, right? Like again, a very 0.04, you will get, right, approximately 0.25 and approximately 0.75. Could you please confirm that these values are correct? And we'll proceed after that in a minute. Okay, how many of you verified those numbers? What were they? Anyone, at least one person in the class should be.
Working on it.
Okay. By the way, in Python is one line of code, np.softmax, right? Of an array, -2, -1, 1, 2. Is one sentence, right? Yeah, what did you say? Find the softmax of this array.
So it's always exponential.
Yeah, always
Max is by default.
yeah. That's a definition. I'm taking you guys. What I'm doing is I'm retracing the history of mathematics of this field by making it obvious to you guys. These things are not written in stone. When you see these expressions in a book, don't just say, oh my God, what is it? Okay, I'll believe it. Right?
So it is point, I got the exact,
Yeah.
it's not 11.26 is the denominator.
Yeah, that's right. But
I
what's
got 0.71, the last one, 0.2397.
yeah? So let me
almost
color
right.
it this way. 0.71. This one is point.
The second one, the second last one is 0.2397.
239. So 0.24. Let's put it 0.24 to the 2 decimal. And the third one,
0.035.
0.035. Little bit off.
The first one is 0.014. Almost zero.
Okay. So my mental math was not bad.
I pasted into the chat too.
Oh, okay. Thank you. So, guys, math is easy. Like all of these things, right? Don't immediately pull out a calculator or a, this. You can actually do it in your minds. Just stare at it and do it. Okay. So what does it say? You realize that softmax, you realize that 0.71 is more than 3 times the second largest one. Right? But now I'll come up with an argument to convince you. While it may be good, because you're trying to pick the bigger probability and say, that's the answer. But in real life, what happens is, suppose you have to tell, I'll give you an example. You have a cow, right? You have a, let's say, a zebra. You have a horse, right? You have a truck and you have a house. And you have to tell this picture belongs to which of these. So what will you end up with? You will end up with 5 values. And when you softmax it, let's say that it was the picture of a zebra. You want the zebra to be big, right? But but there is not just information in the biggest. Jeffrey Hinted's point was, there is actually good learning to be derived from the second best, third best prediction also, right? Because if the second best prediction is a horse, the model has learned not just to identify the zebra, it has learned something semantically. The meaning, between the horseness of the horse and the zebra-ness of the zebra, there's a lot of commonality of characteristics, isn't it? Another way of putting it is, a zebra is just a picturesque horse, nervous and picturesque horse. So it reminds me of a kid's joke I used to play with my daughters. What is black and white and red all over? So the answer is supposed to be a blushing zebra.
Thought it was the newspaper.
Too. Yeah, well, newspaper is a little bit negative connotation when it is red all over. But zebra could do it.
Well, red over means everyone is reading it as opposed to the color red. It's a play on
Right.
words.
Oh, I never got that. I thought that bad news, violence all over. I learned something today. Okay, so you agree, right? There's the second high probability, the third, they all are telling something. So what if we didn't exponentiate it all the way? How can we do that? Suppose we want these outputs to be the output of a teacher, and a student is observing not just the best prediction, the highest prediction, but the second highest prediction and the third highest prediction, and trying to reproduce that order. Because in not just trying to imitate the answer, highest probability, but trying to also reproduce the sequence in a way, do you realize that the student would be forced to understand how the teacher is thinking? Would you agree? Right. So how would you do that? That brings us, do you see the key insight, guys? Right. So now we need a mathematical trick so that the second, third, they don't get suppressed so much. Let's boost them up a little bit. So when you boost them up, like at this moment, the biggest one is a tall pillar, thrice as tall, more than thrice as tall, isn't it? The second biggest is less than 1/3, and other ones are vanishingly small. So, well, vanishingly small numbers are hard to deal with in programming. What if we could slightly smooth it up? Right? Let's just say that softmax is not soft enough. We want to make the probability distribution a little bit more gradual, a softer gradation of it. Yeah. If we are being silly, let's call it the softest max. Right? So if we could do that, so there's a trick for all of these. Beautiful thing in math is, unlike programming, everything is easy in math, right? And so what he did is he introduced a temperature variable. By the way, a lot of these arguments are very resonant with something that you do in a field of physics called statistical mechanics, the study of many particles. So anyway, without going into that and partition functions and so on and so forth, let me just say that there is a bit of history to it. And he sort of used that. He said that suppose I didn't do this, but what I did is I divided each of these numbers by 10. Let's take a number, 10. 10, 10, 10, 10. Now could somebody please exponentiate it for me? Right? So what happens is e to the minus 0.2, e to the minus 0.1, e to the 0.1 positive, and e to the is this number closer to 1.1? Is this number uh, 1.22? Okay, well, this one I was a little off. What is e to the 0.1? Come again? 1.1, and e to the minus 0.1 is, how much is it?
0.909.
E to the 0.1 is 1.10.
And e to the minus 0.1? 0.98. And what is e to the minus 0.2? Do it, guys. Don't do it. Do it on your
Yeah,
machine.
e to the minus 0.1 is 0.9, and to the minus 2.
0.8? 81. So you realize that
0.8, yes.
0.8. So do you notice, guys, that if you divide by 10, right, these numbers, they are not so far apart. So now we say, well, we have damped it down too much. Maybe halfway. Let's try halfway, something smaller. So you see, so the ratio, the denominator, we call the temperature, right? And in effect, what you have done is you have heated up all of these numbers. So they're all bouncing around. right? Equal, more or less with equal energies, right? So let's not heat it up so much. And as you can imagine, this temperature word comes from physics. Let's try 2. How about 2? So 10 is very high temperature. They all practically look the same. Now let's do by 2. So -2 becomes -2 over 2, minus 1 over 2, 1 over 2, and 1. This will be 2.7. Yeah. 2. This will be a half of it, 1.36. This will be minus 0. Well, no. What am I doing? Yeah, minus 0. What am I doing? This is nonsense. Okay. This is 0.5. This will be minus 0.5. This will be minus 1. Right. And now, I hope you're enjoying this little mathematical journey, guys. E to the minus 1 is about 3.5. Tell me, e to the, these numbers would be approximately 3.5, e to the 1.7. I'm just guessing. E to the 0.5. No, e to the 1 over 7 is 1 over 7. No. E to the minus 1 is 0.35. 0.36. Okay, so I was close. 1 over the square root of that will be 1 over 1.7 is approximately 0.6 something. Okay, and 0.5 is 1.7 approximately, right? And this one was a 1, and this is of course 2.72, right? Do you notice? So now when you compare, 2.72 is still bigger, right? But the exaggeration is not as extreme, but it is still, there is certain amount of heating, right? So we learn something. We have an extension to the softmax. And this extension, we will call the, which color should I use? So guys, are you enjoying this mathematical journey? I hope I'm making it very easy. So now we are saying that softmax for a particular Zi would be e to the Zi, the value, whatever. So for example, the softmax for this, suppose this is Zi, is what? You exponentiate it, divided by the temperature, Zi, and then exponentiate it. First divide the number by that and divide it, right? And then you divide the whole thing by the summation of them. So 2.7 plus 1.7 is 4.5 approximately, plus 5.1, right? So everything divided by approximately 5. And that will give you the probabilities, isn't it? So that will mean 0.3, 1/15, right? So it's very small, like you can say 0.14 or 13, 0. Is that correct? 0.18, 0.18. Why am I getting this totally wrong? No, 72. 0.068. Yeah, double of this. Sorry, you're right. And 0.12. Yeah, 0.135, let's say. And this you divide by 5 would be 0.34. Yeah, and this you divide by 5, it will be 54. 0.50. Okay, so 50% probability. These are your p values, right? Exactly, softmax values. So this is e to the, just sum the j over t, right? So you realize that for all values, this is just the denominator, right? With the temperature thrown in. So this is the softmax in the presence of a temperature, right? Heated up softmax. Now, so you say, well, we learned something about softmax and heating up softmax, but what has that to do with our problem? And here comes the last piece of the puzzle, distillation. What it says is just what we said in the beginning. The student need not learn from the reality. The student only has to learn to imitate the teacher, right? So what is the teacher predicting at any given point? Let's say that the teacher for a given input, Zi, produces an input Ti. Right. By the way, Zi may be the hidden state produced by your transformer. Your transformer is there, it produces some logics or some potentials. It's your Zi, hidden state. Now what can you do? You can say, I don't care about, and then you can softmax it and so forth. You can do the softmaxing. It will become probability, isn't it? Right. So let's go through that. A Ti would be softmax teacher. Teacher I would be softmax of Zi over T. Right. You do that. And what you do is a student model will also produce a prediction concurrently. That will be softmax of this is the teacher, right, of the teacher's version, and it will be the student's version. The student version it produces. And now what you do is you say that the loss function was what? Loss function, if you remember, the cross entropy loss was the actual label times log prediction, right? Minus. For any given data point, this is what it was. So forget the summation symbol. Look at the core of it. When the label was 1, cat, log of cat, log of the probability that it's a cat is a measure of the surprise. Now, that is good for when you're training against reality, but you're not training against reality, you're training against the teacher, right? The teacher is training against the reality, right? So what you do is, you say, I don't need to, suppose my master says the probability that it's raining is 0.7, right? I want to produce that probability, not the probability that it's you get it, right? The student thing. So what you do is you replace it with, that's why it's called the distillate probability, log student I. Right, negative loss. I mean, sorry. You see how different is your student's probability from the master's probability, right? You take this as your loss function. This is your distillate loss function. Are we together? Do you see how it is? It's very simple. Student is trying to catch up to the master, not to the external reality, right? If it can imitate the master well, it has achieved his complete knowledge or education. Am I making sense? Basically, that's it. That is all the mathematics there is. And this is the distillation. This process of this is the distillation loss. Now, distillation loss, what people do, and what Jeffrey Hinton in 2015 paper, there's a little bit of subtlety. What he found is that, see, when you set the temperature to 1, right, then what happens is you're doing a hard fit. Means you're not dampening down any of the softmax probabilities, softening the softmax probabilities any further, right? So he called soft distillation when T is greater than 1, like when T is 2 or something like that, take T is equal to 2, that is a soft distillation, right? So you're also learning for the second and the third most likely thing. When you make it T is equal to 1, you're doing a more hard distillation. You're saying, because you know that only the peaks will remain, the others will get pretty suppressed. Right? So he created a loss function by adding both of them up. Hard and soft distillation. And then he found, in his paper, he does go on to say that in his experience, the soft distillation does a far better job. And the hard distillation term is there, but its contribution is small, right? But guys, you got the intuition, right? I didn't, maybe I have done some screw up with the notation, but the main idea you should have gotten. So that is a distillation. So now you look at this model, BERT model, and you ask, BERT is one big behemoth of a model. clumsy model. What is it begging for? A student, a distillation of its knowledge into a student. Are we together? You need a student that makes an even smoother, like snowfall hill, right? Hilly landscape. And how do you do that? Exactly this. This is the training of a student teacher. Am I making sense, guys? That is it. And if you understood it, now when you read a paper like this, it will make sense. This paper is actually rather dense, rather sparse in detail. It starts out by this showing that, models are getting bigger and bigger and bigger, right? As the performance improves, right? It's getting, I believe, as time passes, what happened? Oh my goodness, I went past some things. I'm still on the sentence word. Distil word. Okay. If it is making you giddy, seeing me scrolling, I've asked for your forgiveness. So as time passes, number of parameters in millions goes up. Now in 2023, you wouldn't put your y-axis in millions, you put it in billions, right? So it's exponentially rising. The point called maximum likelihood estimator.
Yeah.
Right. And log likelihood and so forth. So from that, these things can be derived. But one of the things that it comes from that is MLE-based argument, especially forget neural network, simple MLE, like just as a classifier. MLE-based loss function will have an absolute minimum. But when you do straight with the logics and use a classification problem, there are multiple problems to it. Amongst them would be the surface, loss surface loses its convexivity, right? And you do want convexivity. You want one global minima and no other traps around, no local minimas around. And that is not forgetting even neural networks. I'm just talking simple plane or something like that, which is why for classification problem, you always gravitate to entropy, cross entropies. So now we are getting into the deeper mathematics of it.
Asif,
We took a reference statement, we took a statement similar to it, and we took a random statement, right? So reference statement, positive statement, and a negative statement, right? So with the reference and the statement similar to it, you have a positive sample, right? A positive pair. A reference statement and something completely irrelevant, you have a negative pair. So now, this is what this big word contrastive learning boils down to this simple statement. When you do that, you should maximize the surprise when two similar statements, their probabilities don't match. Common sense, right? And you should minimize the surprise when two completely unrelated statements don't match. Isn't that obvious? Right? To say that is literally, there is nothing else. I didn't even leave a iota out of it. That's the definition of contrastive loss. You write your cross entropy function in such a way, you say, I'm maximizing. The loss maximizes when two similar things are wildly different probabilities, right? And I'm minimizing when, they are different. Right. So what can you do? The probability, it's just a classification problem in some sense. Probability that these two are similar is a probability. It should be high for positive case. It should be low for negative case. And that is contrastive learning. So now now you clip, we are doing the clip paper. Is the CL obvious? What could CL possibly stand for?
Contrastive learning.
Good. All right. So, and somewhere they say the word, I hope I got. So now, oh my goodness, where am I? This thing I hate, it keeps jumping on me. Oh no, it jumped up. Sorry. Command F. Okay, you search into this, right?
Yeah.
Okay, yeah, I should smarten up. So now look at the main, now pay attention to me, guys. right? If you're ready and fresh, just pay attention. Look at me at this particular moment. Whatever you're doing, stop doing and look at me. See, if I could convert an image, and this is the beginning of multimodal learning, one of the seminal papers in multimodal learning. If I could convert an image and a sentence, both of them into a vector of the same dimension, somehow I do it. I don't know how I do it. Right? So let's say that I have a neural network with random weights, a transformer with random weights, to transmute an image into let's take a vector, 100-dimension vector for sake of argument, and a sentence into a 100-dimension vector. Right? So you say, well, fair and good. This begins to look similar to the sentence bird, except that there we were taking two sentences and putting them into vector and then looking at the cosine similarity. But here, what we do is we take an image and a sentence that we know are similar. We do the same contrastive learning. An image and a sentence that are similar, image is the reference, and an image and a completely non-sequester, completely irrelevant sentence as the negative sample. Right? Once again, I convert them into vector, very much like sentence, but the same argument. And to the first approximation, there's a little bit of technicality, but pretty much do the same contrastive loss. What will I end up doing? I would now have embedded images whose semantic, whose context is the same as a bunch of words whose content, meaning is the same, into proximity in the embedding space, because I'm looking at, let's say, cosine distance, isn't it? Do you see that, guys? So you ask yourself, well, that is very well, very lovely to say, but how in the world will you find an image and a sentence that mean the same thing? And vast amounts of it. And this is the trick. As always, pre-training has a big element of self-supervised learning. What do? You scrape the web. Now, HTML web developers, what do? When they put an image, they are encouraged to put the alt tag or put a caption there. Nowadays, HTML standard says caption. You can scrape both of those, isn't it? And so you can come up with captions. Now, the reason this is interesting is prior to this paper, the biggest data sets were the ImageNet and so forth, right? In which there were a X number of actual labels. I believe there were 30,000, 32,000 or something. Whatever number it is finite, isn't it? Number of objects. But the world has an infinite variety, near infinite variety of objects, isn't it? So just when you're done with cats and dog, a zebra comes by, right? So what do? How do you deal with that? Yeah. So the beauty of this is you get your image and caption pairs. What they did is they took, they sort of, they said that, see, when we are sort of pollinating the embedding space, right? Let's pollinate with only a finite number, that we'll treat this as a target space, and we'll just take a finite number of captions, right? A caption could be, this is a dog, right? This animal is a dog is a caption or something like that. So you sort of standardize the text that are similar to this, you will mark it as that image marks to this caption. So you essentially create, in the pre-training process, you end up creating sort of label data, but in a self-supervised way. It means nobody is sitting and creating those labels. You don't have an army of people. To create ImageNet labels, literally thousands of people had to work. But here, you don't have to do that. You can do that. So now that you have a lovely label data, do you realize that the rest of the story is one picture says it all? What do? You take the text, you create an embedding. You take an image and you create its embedding. And then what do you want? You want that this particular dog, the embedding of that should be the photo of a dog, right? Those two things should have the lowest cosine distance. Common sense, right? In other words, they should be, forget all of this weird thing. All it means is that in the embedding space, they should be proximal, right? That is it. And if you get this picture, you got everything that there is to this paper. After that, it is, if you look at it, bragging rights come.
Ask the loss today. So how would you make this vectors
the same or close to each other?
Yeah. So what you do in the beginning, so let's say that you have an untrained network. You give it, whether you give it an image or whether you give it, so you have a text image encoder, which emits out a vector, let's say 100-dimensional vector. You have a text encoder, which emits out, just like your sentence vector, something, it emits out a text vector, also in 100 dimensions. Now you know that this, so here's the triplet you create. The positive pair is this text was actually the caption to this image. And how do you, so what do you want to do? You want to make sure that where they land in the embedding space, whatever their distance, using gradient descent, you want them to start coming closer, right? Then the picture and a random statement, they should not be together. They should be far off. So again, they will fall wherever, but then through gradient descent, you want to push them out. Epoch after epoch, isn't it? That is it. And so you keep on doing this little bit, no, millions and millions and millions of steps later, the things will settle down.
So you're pushing apart the third of the triplet from the positive pair of caption and image. The random sentence. Okay.
Exactly. The cosine distances are maximizing the cosine distance, maximizing the cosine similarity between in the positive sample and minimizing the cosine similarity for the negative sample. That is it. That's your loss function. And the beautiful thing is any loss function that you can write as a differentiable mathematical function, magic kicks in. Gradient descent, the whole power of calculus. I mean, many times I've said, and people don't like it, that all of AI is nothing but applied calculus. So whenever you are getting absolutely amazed at this, remember that you're paying reverence to the great God of mathematics. It's all math. Just very simple ideas of math, gradient descent, calculus, minimization, maximization. It all boils down to that, right? In some n-dimensional space, hyperspace or something.
So Asif, if I had to do this link between a picture and another language, right? So then do I have to go from that language to English and then create this embedding? Or once I create the link, I can directly come, say, from Chinese to this dog picture over here, right? How would that happen?
Yeah. So Sachin, there are multiple ways people have done this actually. So it is a given fact that much of the web is English, right? So obviously image caption pairs are much more likely to be found in English. So how do I deal with, let us say, how do I deal with Kannada? A very sparse amount of documents exist. What I can do is I can take multilingual corpus that has English and Kannada in it. Right? Because Kannada has been translated to English and English has been translated to Kannada, isn't it? So what you will do is you will do the semantic embedding of that, right, into the same space. So now what do you know? Into the same space are images, are English sentences, and are Kannada sentences. And so what you automatically ended up creating is a proximity between an image and a Kannada statement, Kannada caption, even though you did not have enough image to Kannada association data. You see that, right? In fact, hang on. The person who created the sentence bird thing, Rem something, why am I forgetting his name? He is now heading another company, just started a company. And one of the things they do very well is this multilingual embeddings, semantic embeddings. In fact, just yesterday I saw his post on LinkedIn. So there we go, guys. So that is one approach you can take. Right? See, Sachin, in this world of deep learning, the general feeling is anything is possible. You just have to find the missing links, right? So you have to put the ducks in a row. And once you put the ducks in a row, it becomes possible. So guys, do you see quite a bit of similarity between This is classic contrastive learning, right? Images and caption. And then the bragging rights are enormous. Zero shot image accuracy. Why is it zero shot? Because there was no training data, no label data to train it.
But
Right?
there was, right?
Well, with zero shot, as I told you, right, is always cheat. There is always a cheat way, right? Under the cover, it's self-supervised. Let's just say that, right? You call it zero shot, and some people say, well, really, you did have a way to create label data. Yeah. But zero shot means no human created label data, supervised creation of label data.
Also, a couple of sessions ago, you told us how languages are different. So Indian language is structured differently to French languages to even English. So Latin languages to even English, which is, I guess, I forget the term, but it's Germanic, I guess, the languages. So if these are all different, how can they create this? How can they say this is all normalized?
A very, very good question. So Shirley says that there are various categorization of languages. Some are pictorial languages like Egyptian, like Mandarin, and so forth. There are languages like the Romantic languages, and then the Germanic languages, and the languages of Indo-Aryan origin, and so forth, Indic languages, and the Dravid languages, and so forth. They have a fundamentally different structure. And yet, how can we do the embeddings? How is this even possible, what I just talked? It has to go, there are many ways to answer it. The way I would like to answer it, and I wouldn't say that I'm the authority, somebody can answer it even better. See, my way of looking at it is through the lens of Noam Chomsky. Noam Chomsky, the great linguist, hypothesized that he showed the universality of all human languages, which is a pretty deep thought. He showed that despite the variety, superficial variety of languages, underneath it has the same structure. In fact, that's how you come up with words like Chomsky hierarchy and grammar that you use in compiler. Did you encounter that? Right? You do that. At least for programming languages, you have that. So anyway, I'll just finish my thought. In fact, so if that hypothesis is true, it means that if you think of the H.G. Wells story, the Valley of the Blind, right? Or imagine an experiment like that. You throw a bunch of young children into a valley, and they live and they grow a language of their own. Then theoretically, they will develop a language not dissimilar in structure to any of the other human languages, because they all share the same universal structure. And Chomsky went on and has hypothesized that it has to do with our brain, the mechanics, the physiology, the neural firings of the brain are, the structure of the human mind is the same, is universal. And therefore the languages we create are universally alike, right? And I think that is the reason why we can do cross or multilingual learning or embedding, because the semantic is the same, right?